Peki. Şöyle. Se. Çek. Geliyor. Bu da çalışmıyor. Nerede o çocuk? Hı. Temiz. Bence başla artık. Kim bekliyor?
Hı?
Kim bekliyor?
Hocayı
Hoca da geldi. Çeyreğe mi kaldı? 5 dakika dedik.
patron seçim.
Tamam yani o şey yapsın. Bilmiyorum Zoom'da kaç kişi vardı. Zoom'da biri var. Hı?
Yes,
Zoom.
bağlanmadım.
Okey. Bir kişi var. Tamam. Aç aç. Aç artık.
Everyone. So we have in the morning industrial applications session. So we will start with Dr. UPHUKVIII. He did his PhD at Ankara University, and currently he is postdoc at University of Estonia, and he will talk about the company electron beam technologies. So let's welcome Dr. UPHUKVIII.
Thanks.
Floor is
Salim.
yours.
Can you hear me? Good morning, everyone. My talk will be about the electron beam application for industry and newly established a company that are working on electron beam and its applications. This is the outline of my talk. I will give a brief introduction, brief information about the electron beam and its technology, and I will give some example of the electron beam applications, and then I will present UPHUKVIII company and what are we doing in this company, and I will conclude my talks with the company future goals and prospects. As you know, electron beam is being widely used in industry, health, and science for various applications. And the beam energy is ranged from the kilo electron volt to tera electron volt. For example, if you are using scanning electron beam microscopy, and electron beam energy will be about 10 kilo electron volt, or if you collide the particles to search new physics, and the electron beam energy will be about the TeV scale, like click. If we turn the industrial electron beam, the energy is about 10 kilo electron volt to 10 million electron volt. The maximum allowed energy of the electron beam is 10 million electron for industrial usage. Because of the higher energies than that, could potentially induce the radioactivity in the material. Electron beam is also a source of X-ray. Electron beam technology. If you have a gun and you should produce, you can produce electrons and forming or shaping to them. And in the beam transport line, you steer and focus or scanning the electron beam, and you use the targetry system for the manipulate the workpiece for the different application. Why are we interested in the electron beam applications? The electron beam market value is about $50 billion at 2011, according to International Atomic Energy Agency report. And you see here the application like surface current, wire, cable, tubing, shearing film, tires, other or services. And if you look at the Turkey import values about the electron beam, for example, in 2021, the X-ray tubes and its components market and import values is about $60 million, and it's a huge amount. And because this is the important. And so, what are the electron beam applications? You can see some applications from this slide. For example, additive manufacturing. If you hit the workpiece with an electron beam, it's melting, and you can give a form, give a desired form, like here or here, and we are using this instead of CNC machine because it is impossible. Some part is impossible to produce in CNC machine, or hard to be produced in this machine. And the another application is welding. You can use the electron beam. Put together two metals, different time or same metals together with this application. And another one is sterilization. You can use electron beam again, or therapy, or lithography, and so on. And if you look at the company overview, the ETH was founded by 4 physicists in the last quarter of the 2021, and it has 5 employees, 1 physicist, 2 mechanical engineer, 2 electrical engineer. And what we are doing in this company, we are working on electron guns and electron beam processing. In short term, we are planning to produce RF power generators, like magnetron, or amplifiers like traveling wave tube. And also in short term, we want to produce X-ray generators. This is our first machine. You see from the picture. This is the electron beam welding machine. This machine can be provide 50 kilo electron volt beam energy and 40 milliamp beam current, and you can weld up to 10 centimeter diameter and 20 centimeter height workpiece in this chamber. This is the advantages of the electron beam. For example, you can weld deep and thin welding, or clean welding, and you can weld complex geometry of this in this machine. And also we try some welding trials, and you see the injector part of the gasoline engine. Its material is 439 stainless steel type material. We weld two type, and full penetration and partial penetration, and we test the parts was tested by the independent company, and result was successful. You see the radiological and liquid penetration and magnetic particle test, and all test was successful. And we also tried to measure the penetration depth, or in stainless steel, this type of stainless steel, and the measurement was 2.9 millimeter in this material. And also we tried to different welding techniques, like peripheral and butt welding of stainless steel. And also we welded different type of metals different type of metals like stainless steel to titanium aluminum vanadium alloy. In here, we weld the 0.1 millimeter diameter wire to 0.7 millimeter diameter stick together. And the wire material is nickel chromium alloy, and the stick was the inconel. You see from here the heat input on the pilot beam of the on the workpiece. What is our ongoing projects? We start to produce 3 different types of electron guns. The GET, OGET, and YGET. The GET means is low voltage electron gun, and it will provide 30 kilo electron volt beam energy and 100 microamp beam current. And we are planning to use tungsten cathode in this gun, and you can do scanning electron microscopy application with this gun. The other one is the OGET. The meaning is the middle voltage electron gun, and it will provide 60 kilo electron volt beam energy and 10 milliamp beam current. And again, we will use tungsten cathode in here. And you can use this machine for the electron beam welding or X-ray source. The last one is the YGET, and meaning is high voltage electron gun, and it will provide 150 kilo electron volt beam energy and 25 milliamp beam current. In here, we are planning to use dispenser and lanthanum hexaboride cathode in this machine, in this gun. And again, you can use this machine for the electron beam or TEM application. And also, we are planning to produce beam scanning, focusing, and diagnostic system. Also, we produce the control system for this machine. This is the ongoing projects and our goals. We want to propose new projects with the electron gun, like as I mentioned before, X-ray generator or RF power generator or amplifier. Also, we worked on a surface processing with electron beam. As you see from here, 30% surface hardening has been achieved in stainless steel 304 type metal, and depth was about 400 micrometer. And also, we are planning to produce vacuum gauge beam diagnostic equipment in-house. So products, as I said before, we have an electron beam welding machine, and we are doing welding services with this machine to domestic industry. And also we want to promote our domestic electron beam welding machine to the market. For example, you see an example like this machine. The machine provide 60 kilo electron volt beam energy and 33 milliamp beam current, and its price about 265,000 euro. This price was about 2019. And if it turns the electron guns with the right strategy, we are planning to compete with foreign companies, and we are searching the places what we are inactive. and we put the another two example about the electron guns. These guns produced by the Kimball physics, and for example, this machine provide 1 kV to 30 kV electron beam energy up to 5 milliampere beam current, and its price, its basic system price is about $64,000, and the other one is the other one provides 1 kilo electron volt to 100 kilo electron volt beam energy and up to 1 milliampere beam current, and its basic system price is about $100,000. And as you know before, and we collaborate with UPHUKVIII on the two projects. One of them is the Proton Linux project. We are planning to produce the 800 megahertz radio frequency quadrupole, and we are planning to produce 2 million electron volt proton beam, and we will use for this machine for the pixel application. And the other one is the electron accelerator project, the Rhodotron project, and we are planning to produce 1 or 2 million electron volt energy electron beam, and we are planning to use this machine for the medical sterilization and cross-linking of the cross-linking of tires. This is the map of our experience and our company goals. And if you want to have an electron beam or proton beam, you should know vacuum, material science, high voltage, mechanical, thermal, and their simulation techniques. And for example, if you have an electron gun, you can use electron beam welding or electron beam hardening application. And the other way is you can produce the X-ray generator or RF power generator. And it's same for the proton beam. If you have a proton beam, you can do these applications like focused ion beam, proton beam therapy, and so on. ETASH is newly established, and we want to commercialize the prototype products, and we want to grow up our team, and we want to expand our product portfolio. And also we are working, we want to work on the particle accelerator related technologies such as RF vacuums and simulation. And that's all, and thank you.
Thank you, Dr. Kaya. So we can get questions from the audience. We can get questions from audience or Zoom. Is there any questions, comments? Yeah.
You are developing Rhodotron. As far as I know, it's IBA product. So did you get the permission from IBA or?
As I know, the patent of this machine is over 20 years old, huh?
More than 20 years.
More than 20.
Yes.
Then,
so the patent is expired? Or
yep.
Okay, that's very good. Then second question is, how about the material for cathode material?
say again, please. Sorry.
Cathode material.
Yeah.
Are you purchasing or are you making the cathode?
No, we are selling.
You're making yourself?
No, we are selling the cathode.
Buying.
Buying, yep. Sorry, buying.
It's expensive.
Just we are buying the tungsten. You mean the
This-
wire of?
No. Dispenser cathode I'm talking about.
Or we are buying again.
No.
We are not producing.
So tungsten, no, what a cathode material you are making by yourself. Is it correct?
As you heard, we have many different types of cathodes. The tungsten wire itself is bought from abroad. The lanthanum hexaboride is also bought from abroad. In Turkey, it is possible to make dispenser cathode. But for the very first test, we purchased from abroad, but we also tested locally produced dispenser cathode as well. When we commercialize, we will see what we are going to do. We have not yet decided, but I can tell you that it is possible to grow a crystal and it is possible to build a dispenser cathode. Whichever is economically feasible, we will choose that path.
Can you pass the mic to me?
Thank you for the talk. I was wondering if you have some timeline for the sources you plan to develop. You were mentioning about 3 different electron sources.
Yeah, we have 2 years for the production and 1 year for the commercialize. Totally 3 years. Yeah.
Is there any more question, comment? Maybe over Zoom? No?
Hello? Hi, I don't know if you can hear me. Alessandra Lombardi here.
Yeah.
Yes,
Can you hear
Alessandra,
you?
we can hear
Oh,
you.
okay. Thank you. Sorry. So thanks for the nice talk and really congratulations on this really ambitious program. I have a question on the RFQ. What machining tolerances could you achieve? What are the planned machining tolerances? If you could expand a little bit on this detail.
I'm not expertise on the RFQ, but maybe you want to ask us?
Or no worries, I can contact you later by email or something like this, okay?
No, we are answering. Just
Oh,
can
sorry.
do it?
I'm Görkem. We produce a cold model with copper for the RFQ production test, and I think we achieve below 20 microns for the production machining tolerance.
Thank you. This is very good to know. It's very good accuracy.
So is there any more questions, comments, especially from Zoom? If not, let's thank our speaker again. Okay. So our next speaker is again from a Turkish company dealing with accelerators and detectors and its applications. So it is IRARET's Innovative Radiation and Detector Systems Incorporation. And we have Abdullah Çoban with us. He's going to present the company and its applications to Turkish science and R&D. He's getting prepared.
Şu tepe. Ses. Ses. Ha, okay. Hello, good morning. My name is Abdullah Çoban. I am here to represent Redis company as a R&D manager. Ses. Okay. I will talk about today ongoing projects and services of our company. My talk title is, it's too long, but if I summarize, Redis applications from Earth to space. So, the first thing, who we are. Redis is high-tech spin-off company operating in nuclear technologies since 2013 in Technopark Istanbul, established by Professor Dr. Behçet Alpat. We are working on three main activities. These are development of metal radiation interaction softwares, and innovative radiation detectors R&D studies, and also radiation hardness assurance services. Our ongoing projects under these three main activities are MRASIM space radiation analysis software, supported by TÜBİTAK and COSGAP, mini SPT mean space particle telescope. This project is supporting by TÜBİTAK TEİDE, and IRADCAL is part of mini SPT but lower cost and smaller size version. This project is supporting by TÜBİTAK Space and also Turkish Space Agency. IRADCAM is medical purpose gamma camera. This also supporting by COSGAP. And finally, PDOS, new generation personal dosimeter. Except for these, our projects, we are also giving services for radiation matter interaction using the nuclear facilities in Europe and Turkey. The service areas is for this purpose, space applications, nuclear or Earth-based applications, medical and aerospace applications. Today, I will talk about summarized information of these our projects and the services. Oops, sorry. The first project is MRASIM Space. MRASIM Space is first product of MRASIM family. This software is designed for space radiation analysis purpose. MRASIM Space is carried out with partnership of three institutions. These are IRADETS, INFN spin-off company BMIT, and also INFN itself. MRASIM Space with user interface includes all process in order to perform space radiation analysis. This software, MRASIM needs 5 key input to perform analysis, basically. These are defining of the geometry, the defining of the source particle, analysis parameter, physics definition, and other. After complete this, the user not necessary to know any software language to use this and making the radiation analysis. After defines this parameter, calculations start, and when finished, the graphical display will show the result to you. And these are just some examples from the user interface. If we talk about the backend side of the program, this backend side of program is created by using different platforms. Source code developed using the C++, cross-platform distribution using CMake, GUI and data analysis part developed using the Qt5, 3D engine and CAD processors developed using the Open Cascade, and the Monte Carlo-based physics simulator, of course, using the Giant4. This diagram shows the basically show the what is the program algorithm. If we talk about also some features during the runtime for the users, as I said, user can define the geometry the importing the step file or creating using the user interface, or if user has any GDML files which worked before, it can be also import for the analysis purpose. Also, there is always 3D geometry interaction using the program. You can assign your material using the user interface, just mouse click actions. And there are massive material database in program. But except for this, if you want to define the new material, there is option to using the interface. And another feature is you can assign the material with multiple choice. For example, if you have 100 or 1,000 geometry which they have same material, you can assign in once. And defining of the particle source is, as you see this picture, you can see the shape, size, and position in the GUI. And there are many also multiple analysis option to start your simulation. If you talk about the analysis, MRASIM especially designed for the space radiation analysis, and these analysis functions selected for this purpose. These are, you can make analysis for total ionization dose, energy deposition, fluence for primary or secondary particles, path length analysis, LET analysis, LET mean linear energy transfer, deposit charging, equivalent dose analysis, and non-ionizing energy loss analysis. These gives the 1D histogram with statistical numbers and the scalar values. Except for this, if user needs any general information from the geometry, user can define full body or part of the geometry using the 3D mapping calculations. For this purpose, there are 4 different options for 3D calculations. These are ionizing dose mapping, energy deposition, flux and deposit charge. These are just example from the 3D calculation results and the other analysis, 1D histogram. In addition, our software project, we are also working on the particle detectors for different fields. The first project which I talk about is mini SPT. This mini SPT space particle telescope now supporting by UPHUKVIII, and aim of this project is development of 3U CubeSat size, radiation tolerant, low cost, and high performance space particle telescope. During these R&D studies, we want to measure with this device flux, energy, direction, using the particle separation for different type particles, which are electron, proton, heavy ion, or galactic cosmic rays. And in the energy range of the 100 keV to 1 giga electron volts. This detector actually consists of the three different sub-detectors. These are, the first detector is silicon pixel detectors. As you see in this right picture, there is first scintillator and second scintillator. These are time of flight. Between them, there is silicon pixel detectors. And after that, also there is calorimeter. If you imagine the particle coming from through to here, all interaction will be there. The silicon pixel detectors have been used in the CMS experiments. These silicon pixel detectors is very well position resolution and also flux capabilities. It's also highly radiation tolerant. Silicon pixel detector will be measured tracking of the particle with also DA and DX measurement. The second detector system is calorimeter. Calorimeter consists of the scintillator crystal with CPM arrays. This part of the detector will be measure energy deposit with also DN and DX measurement. And last part is time of flight. Time of flight also consists of the two very thin scintillator with single CPMs. CPMs, by the way, silicon photon multiplier. And this scintillator, this detector have two main aim. The first is when particle hit the first scintillator, the data acquisition of the silicon pixel detector will be triggered. And the second aim of this detector, of course, it will be measured the time of flight between these two parts. And also in itself will be measured the DA by DX measurement. If we look to some capability of these detectors, these graphs, the calculation actually is performed using the GAN4 simulations. These graphs coming from each part of the detectors is a separated way. As you see in the graphs, if we give some examples, for example, these graphs coming from this only single SPD detectors. In the low energy range, also even in the low energy range, there is particle separation easily between the electron protons and the, for example, heavy ion. This is for carbon, for example. The last two graphs coming from the time of flight. This part electron and for proton and the zooming version, and this with also ions. We can see the limit of this detector and the achievements if we see from the GAN for results. As I mentioned before, these results coming from the for each separated module. If we combine these detectors using the special algorithm and the data acquisition system, also we will get more precise and important valuable parameters from the detector itself. Second detector system is erratical. This detector system is actually part of the mini SPT's calorimeter system, but different size calorimeter and different size CPM array. This detector actually produced on request. Turkish Space Agency requested this detector. This detector has been selected for payload within scope of Turkish Space Agency lunar mission in near future. The main purpose of this detector is will be measure energy spectrum of electron, proton, gamma ray, and galactic cosmic ions in energy range of 100 keV to 400 MeV. Other detector system is ERATCAM. This detector system medical purpose radiation detectors. And the detector system is designed as a portable handheld gamma camera system. Detector consists of cube-shaped scintillator crystal with two-side CPM array. The main purpose here, not only measuring of the energy spectrum and dose rate of the detector, also we will get the image reconstruction from the tumors which emitting radiation by using the radiopharmacy. And these tables actually defined beginning of the project. The main parameter here is spatial resolution. We were want to do this spatial resolution before of the with the preliminary some works before beginning of the project less than 2 millimeter. But after that, when we start on this project, the first thing we perform the simulation calculations and get some rave data using optical propagation on the GAN4. And we use some special algorithms and also upgraded this special algorithm, and we are able to get less than 1 millimeter resolution. This is really good resolution for this kind of system. Also, except for this Jan4 simulation, we started to make some laboratory experiment using the point source with offline measurement. And when we get the raw data, also we are able to get same value, almost same value with the experiments. And the last detector system which we are working now on is a PDOS, personal radiation dosimeter, new generation radiation dosimeter. This dosimeter system is actually based on scintillator crystal and the CPM based. There are 3 different size and material scintillator crystal, and with the CPMs. The main proposal to this project is the very small size variable producing of personal dosimeter. The type of radiation will be detected with using this personal dosimeter is gamma, X-ray, beta, and also neutron. And these are some expected values, not actually expected value. We almost get these values because this project is almost done. And we are finished the first prototype, and we will start the commercialized process. So, as I mentioned before in the beginning of this talk, except for the R&D studies, we are also giving some services for radiation hardness assurance tests. All kind of materials, active or passive electronic components, mechanical parts, or composite material, which to be used in the radiation environment, we are able to make tests and prepare the report for this purpose. During this process, we are using some facilities in generally in Europe, and also, if necessary, also we are using in Turkey. And except for these facilities, we have 2 systems in our laboratory to make, before go to this radiation facility, to make some simulators. The first system is the laser radiation system. This setup is particularly useful for the radiation sensitivity mapping. For example, if you have an IC or another active component, and you want to test for using the radiation laboratory. Before go to the laboratory, you can make test your electronic evaluation boards, your softwares, because it will be, you can get, actually you can, if you have any problem in your system, you can see before your system, and you can fix, and you can go to the laboratory. The other system is a solar effect simulator. This solar simulator is used for control testing condition on the Earth study effects. And for this purpose, we designed a system with using the LEDs, and up to the 400 nanometers, we are able to give to the solar effect up to 2000 sun hours. These are my talk. Thank you.
So is there any questions, comments from the audience or Zoom? So actually, I have a comment. When you check on Jan4 the energy disposition, do you check peak energy deposition density, which can be critical for not to melt the material?
Sorry, I don't understand.
So when you check the energy deposition,
yeah.
So you need to check also the peak energy deposition density in a cubic centimeter or in a gram of material. Otherwise, if it is in a critical range, it will melt.
For which detector system?
For any of them, when you check energy deposition, don't forget to check peak energy deposition density in.
Yes. This is there is actually two needs for the making energy deposition. The first, to get the total energy deposition, and we are just some all the data, but also we are able to get the for each peaks and the interested energy, and
Okay, so I haven't seen it on the slides.
There is
you are aware of it.
Actually, these data, all GEANT for simulation for detector system, we integrated the optical photon interaction, and this process normally not inside directly GEANT. There is external code, and after that, the results seems gives as a totally. But also the defining of the material or other works, we are checking this.
Good. Any
Hello. The very first software that you presented, the radiation simulator, how long did it take you to develop that software?
Yeah, the project started with actually, this project is company first project, started 2030, and the middle of during this period is just stopped because of I don't know, some reason. But last 2 years we really work on that, and the product is finished and ready to use for commercial purpose now. And beginning of October, almost 25 INFN station will be start to use. Also, there are some requests from the Turkey, TÜBİTAK Space, TAI, and other companies. And it takes too long time to prepare. And after that, also our next projects about the software part, we are now starting to work on MRASIM Earth-based applications for nuclear facilities or other. And the other is nuclear medical. We will work on this in near future.
Okay. In your detectors, you are using some electronics. Obviously, you must be buying that from somewhere.
Yeah.
You are designing your own PCBs, I presume, to make the thing.
For this, actually, the main problem in during the simulation using the GEANT for defining of the geometry, we are just directly import any CAD design step file. If you have, if you are mechanical engineer, create just importing without any limitation about size or geometry type, and you can define the material.
Are you purchasing the scintillator crystals, or you are producing them?
Scintillator part. Sorry, I was thinking about the
okay.
rest.
I understand.
Yes, we are purchasing from.
Whatever. How about the calibration of your detectors? Are you using a source, or do you need some sort of a beam out of an accelerator?
Yeah, we have for this, the first we are using, actually for the calibration, the first we integrated the simulation, and after that check results with non-detector system. After that, we used our system using the laboratory source. And the third one, we will make a test using the accelerator, which is we talk with the TARA, the medical electron linear accelerator. We will make some tests using that machine.
Okay. Now with my commercial hat, maybe we can also provide you some some beam time.
Of course, we want.
Thank you.
Thank you.
Good collaborations being put. So this is good. So we have İsa Hoca on Zoom. He wants to comment or ask a question. İsa Hocam, buyurun.
Okay, thank you. The first question is about software copyright. I mean, when you are using GEANT or other open sources in your commercial software, how do you deal with the copyright of the open sources program? The next question is about your calorimeter. What is the size of it? And it is long enough to contain 1 GB proton. Do you have any test on protons? or only simulation? Last question is also, did you test your part for radiation hardness before, provide it to space agency? Thank you.
Thank you. I understand first question, but I didn't understand exactly the second question. I can give answer for the first. About the license issue for the Giant4 part. Yes, it's open source program, but there is no limitation for the commercial part because we made some agreement. Also, except for this MRAS SIM, there are another commercial product in the world. The name is FastRat, with Thread company from France. They are also using the Giant4 and their algorithm. There is no limitation to use. But can you repeat, please, the second question? Because
second question was about the size of your calorimeter. How long? I didn't see any number.
Okay, size of calorimeter, it's about 3 centimeter cube.
Is it enough to, measure the proton energy, or you are trying to implement D over Dx to measure the proton energy?
Yes, it's enough because we are not using plastic scintillator. We are using gallium arsenide crystal, and the energy deposition very well than the others. And after making some simulation and test, until some point there is no saturation. We can get that numbers. Normally, we were thinking to go upper that, but this is the saved region as I simulation. So it's enough.
Any test with protons?
Not yet. We are now designing our electronics. We use some commercial cost electronics with CAM product, but now we are preparing our electronics. After that, in probably beginning of the 2023, we will make tests in the UCL laboratory with proton beam or heavy ions. Also, if we are able to use a proton accelerator in Turkey, we will do here also.
Nice. Last question was about, since you are planning to use it in space, do you plan any test your parts, for radiation hardness before sending it to space? As you provide services for radiation hardness, did you test your part also, before giving it to space agency?
We made many tests for this purpose. We haven't tested our electronics yet, but the last 6 months ago, we made a test for Aselsan company, for example, using UCL laboratory in Belgium for their electronics. We are able to do, and we want to help to you if anyone requests this. So that's all.
Okay, so thanks for the questions, and let's thank the speaker again. So now we have our own Veli Yıldız from, he did his PhD at Boğaziçi University and CERN, and then he continued his work at CERN in ACFO. So he's going to talk about the new light proton accelerator, a company which I am also working for. So let's have Dr. Veli Yıldız or Veli Kadimo with us.
Sesim geliyor mu? Mikrofon açık mı? Tamam. Hi everyone. Well, first of all, thanks a lot for inviting me for this Congress. It's very nice to be here and see all of you again in person. Today, I will tell you a little bit about the project we are running at EVU Adam. Okay, first, short introduction about myself. Well, some of you know me as Veliko, some of you know me as Veli. So I have just small clarification. I have two nationalities, two names, hopefully not two different personalities. I've been working at CERN with Alessandro Lombardi, who gave a presentation yesterday. And I worked there for 5 years, and I was involved in UPHUKVIII project. And at UPHUKVIII, I participated in different studies and operation of the LINAC as well, from beginning to the end of the LINAC. So just after the 160 MeV achievement, I made the transition to AVO Adam. During my fellowship at CERN, I was also involved in high-frequency RFQ project. This was presented also yesterday. I was running some beam dynamic simulations and trying to make sure that this RFQ would really work, trying different simulation codes and comparing their results. And I was lucky enough to commission this mission actually when I moved to AVO Adam. At AVO Adam, I've been working there since 2017, and I'm in the physics group, accelerator physics group, and I'm the deputy group leader of the physics group. At the moment, I have 6 accelerator operators working with me, and I have 2 beam physicists working with me. One of them is here, Salim. And I also took responsibility as a coordinator in the company. So I'm one of the 3 accelerator run coordinators. For this responsibility, we coordinate operation together with the other accelerator run coordinators. We are from different groups, one from RF, one from beam diagnostics, and one from beam physics. And I am responsible for the beam commissioning of the LINAC. Sorry. So the company, AVO Adam, we have different offices in the company. We have our parent company, it's Advanced Oncotherapy, AVO, and their headquarters in London. The AVO, Adam, it's accelerators and detectors applied to medicine. This is a CERN spin-off company, and this is where we have the R&D facility and R&D team as well. And we are in Switzerland, in Geneva. And we have now our testing and assembly site in the UK. And we are somewhere in between Manchester and Liverpool. There is STFC Research Center, Daresbury, and we are using their facility to build our first machine. And we have other offices in Netherlands and USA, but with minimum number of people. If you want to get some more information, I put a link here. You can go and learn more about the company. And few words on the product we are developing. So what you see here is the full product we are developing in the company, starting with the proton injector assembly, then the accelerating structures here. We'll talk more about those. And we have high energy beam transport. And at the end, we have a patient treatment room. And at the moment, we are building this full system in the UK, in Daresbury, for tests, and hopefully afterwards to treat a patient. The product we are developing is called LIGHT. It stands for LINAC for Image Guided Hadron Therapy. And this machine will be used for the hadron therapy. Few specifications. In short, the length of the LINAC, it will be about 25 meters. And maximum energy will be 230 MeV, but we can change the energy down to 70 MeV using electronic methods. So just switching off the cavities, we can go down to 70 MeV. The output beam current, peak beam current, pulse current, we are looking for is about 40 microamp. This is quite a low beam current compared to some LINACs in research centers injecting to maybe synchrotrons. This is enough for us to treat patient, and this is more or less the beam current the proton therapy needs. In terms of pulse length, we can change the pulse length between 0.5 and 2 microsecond. And RF frequency we are working is about 3 gigahertz. And we can go up to 200 hertz beam repetition rate. Few things to mention about the product is we can change the intensity of the beam and energy of the beam from pulse to pulse. That means we can change these parameters in 5 milliseconds. And in our Linux, we are using only permanent magnet quadrupoles. There are about 70 permanent magnet quadrupoles, and there are no electromagnets. There is a nice video here. If you want to go and you can go and learn a bit more about this machine. Let's talk about a little bit the structures, accelerating structures. The first accelerating structure is the RFQ. This is the first RFQ was developed and built by CERN, and it was commissioned again inside CERN, but by the company. And the second structure is SCDTL, side-coupled drift-tube Linux. Maybe you cannot see clearly, but there are accelerating tanks here, and the tanks are coupled to each other from the side. This is where the name comes from. And between the tanks, there is a tiny beam pipe, and we have small permanent magnets to focus the beam. And one module of SCDTL, it looks like this. There are 4 modules in our machine, and there are different number of tanks depending on the design. It can be 7, it can be 11. The next structure, so here is the RFQ, SCDTL 4 modules, and then we have CCL structure, 15 of such modules with different length and different cell lengths inside. And CCL stands for coupled cavity Linux. And we are using different structures along the accelerator to be more efficient in terms of acceleration. And one important thing to mention, well, we didn't come up with the idea of these structures, and the idea of these structures are coming from academia, and we are using this idea, but we did except RFQ, we did the design of the other structures in the company, and maybe some improvements using the idea of these structures. What you see up here, these are the modulator klystrons, and they are feeding the Linux with the RF power so that we can accelerate the beam. In this figure, they are shown right next to the Linux. You can put there, but in Daresphere now we put on the 2nd floor, and we send the RF power with waveguides downstairs. I was telling you that this is about 25 meters. Just to give you some idea, we will go up to 230 MeV in 25 meters. This is quite a high acceleration. The design of this Linux is much different than conventional Linux because its purpose is different. So we need smaller beam current. This is why we could go to higher frequency to make the structures smaller, shorter, and accelerate the beam at a shorter distance. We will go to 230 maybe in 25 meters, just to give you an idea from Linux 4. Linux 4 is about 90 meters, and it accelerates the beam 260 MeV. This doesn't mean our machine is better than Linux 4, obviously. It's just the purpose is different. But if you design a Linux especially for that purpose, you can make big changes and make it much shorter. So high frequency for protons, it's a very good idea, but obviously it's challenging. It's the first time anyone put these 3 structures together, RFQ, SCDTL, and CCL, and accelerated the beam, proton beam to high energies like we did with all Linux solution. What are the some advantages? I won't list all of them, but you can gain higher energy at a shorter distance, and you can have a smaller footprint, and you can install it to smaller places. But okay, smaller size is also a disadvantage because you have a smaller beam pipe aperture, which will cause difficulties in operation in terms of transmission, and in terms of production tolerances and alignment tolerances, it's quite difficult as well. To give you an idea, along the Linux, starting from the RFQ, the biggest beam aperture we have in terms of radius is 3 millimeters. Just to, again, to have a feeling, this strobe I have in my hand, it has 7 millimeter diameter, and the biggest aperture we have in the Linux is smaller than this one. So imagine 20 meters of such a pipe, and you want to transmit the beam all the way to the end. It can get quite challenging. So we are trying to develop an industrial product, but we want to satisfy the medical standards. And how this can be done? Obviously, there are many things that affects, but I just want to focus on these topics here. First, you need to do feasibility study. You need to demonstrate that this method we are trying to apply with high frequency cavities would work. And this is what we have done in Geneva between 2016 and 2019. We'll mention about this. And there is a very tedious product design and development following quite strict processes with the documentation. And then the last, after production of the cavities and all the structures, you can start building the machine, test it, and at the end you need to go through some very strict validation and verification process to get the medical certificates. And this is what we are doing at the moment. We started in 2020, 2019, and this is being done in Daresbury, UK. And we are building our beam production system there, and afterwards we will also have medical treatment. We also have medical treatment area being built, and as I said, we are planning to perform treatment there as well. One very, very important thing when we talk about accelerator projects, you need expertise in the team, and you need a very strong collaboration among these teams. And in the company, we have quite a big range of expertise. There are many people in the company, like me, coming from academia, from research, and working on this machine. We have expertise in beam physics, RF, beam diagnostics, high power electronics, vacuum, cooling, mechanical engineering, control system, software engineering, and so on. I just brought the most important ones here. And we have more than 80 people working on this project for design, development, and installation and testing of the machine. So to give you an idea how much manpower and expertise is needed to build such a machine, even if it's 20 meters. Now I'll go a bit back in time and tell you about the feasibility study we did in Geneva. It was very important for us to demonstrate that we can put all these structures together and accelerate the beam. First of all, we had to convince ourselves that we could do it. Here we have a L-shaped ion source. So source, we call it proton injector, ion source, and the low energy beam transport. And then we have radio frequency quadrupole. And the one we used, it was developed by CERN and installed for this on this, let's say, prototype machine. And we have 4 different SVTR structures, modules, and we have here 2 modules. It's not very clear, but we have 2 modules here for the CCL. And these are the modulator klystrons here, sending the power to the structures. And we have IoTs for the RFQ and waveguides, 4 waveguides feeding the RFQ. And we performed many different tests in this machine. We didn't install all the machine at once. We went step by step, installing a part of the machine and putting a movable diagnostic test bench to measure the beam properties. In 2016, we were at 40 keV, and 2017, 2018, and at the end of 2018, more or less, we went to 52 MeV, and we demonstrated that we can accelerate beam up to, well, we can accelerate the beam using all these 3 different structures. And after we demonstrated this, we put all our focus to Daresbury, to our first system. I put some links here. There are some papers related to this work. You can go and have a look. I will mention a little bit about the measurement test bench we are using. So also, Alessandro mentioned yesterday, it's quite common when you commission Linux, at least Proton Linux, to put a dedicated test bench to measure beam properties, because in the Linux, you might have very limited number of diagnostics, permanent diagnostics, and they will not allow you to measure everything. And going step by step and measuring the beam properties at different places, it will allow you to understand how the machine is working and what the beam properties are. The test benches, they usually look like this. You can have a straight section here and a dipole, and you can switch on the dipole or switch it off. If you switch it on, you can send the beam to spectrometer arm here. This way you can measure the energy, you can measure the energy spread, but also you can separate accelerated particles from unaccelerated particles. That's also important to measure. And you can put whatever devices you want here, depending on what you want to measure. But what we use at the low energy, we have diagnostic boxes with the slit and Faraday cup inside. We use those for beam profile measurements and emittance measurements. And in between, we have beam position monitors. And we also have time of flight system here with using three phase probes. At the end, as a dump, we use Faraday cups, and we also have another diagnostic box here with the slit and Faraday cup to measure the beam profile if you want to measure the beam energy and beam energy spread. We also have quadrupole magnets here. Depending on design, you can put them into different places, but these quadrupole magnets are quite important to change the beam properties for different measurements. And also at high energy, you can change the design of this test bench, because at high energy, we cannot use these diagnostic boxes anymore. And we can apply different methods for emittance measurements, for example. And at high energy, we have another beam profile measurement device here. We call it fiber scanner monitor, and we use quadrupole variation method for the emittance measurements. So this is the general idea of the test bench, but as I said, you can change the design depending on your needs and depending on your energy. But it's quite important to measure the beam intensity, energy. We do this with time of flight and the spectrometer. We measure 1D profile and 2D spot size as well. After some energy, we have scintillating screen. Transverse beam emittance, beam position, and energy spread. There are some papers here. I put link again if you want to go read more about the test bench we used. So I will give you very few results from the beam commissioning in Geneva. Well, I put some results related to RFQ because I found it interesting when we did these measurements. When we were performing emittance measurements, we observed some strange shape like this in the phase space. So there was a hole here, and it was appearing on the right side and on the left side afterwards. We did some simulations and tried to understand where it was coming from. And when we tried to steer the beam left and right, here you see the emittance of the RFQ in red and the measured beam before the RFQ in blue. And if you steer the beam towards left in simulation, this is what you get after the RFQ, and this is what we measure. If you steer the beam towards right in front of the RFQ in simulation, this is what we got, and this is what we measured. So they were they had quite a good agreement. It's interesting to see all these holes after the RFQ. It's amazing that we can reproduce it in measurements and simulations. This is showing us how nice the modern simulation tools are. And if you center the beam on this acceptance, then you can have a solid beam in the phase space after the RFQ. And this is a comparison with what we expected and what we simulated through the RFQ. The RFQ worked amazingly well in terms of transmission and its performance. And all the results we got, they were matching quite well with the simulations. Now I will jump to the end of the LINAC, and this is one measurement I enjoyed a lot doing. We wanted to demonstrate energy modulation, so we did some zigzag in terms of changing the energy from pulse to pulse. We were jumping up and down, and we said let's write AVO Adam with the energy. So we programmed the low-level RF boxes to change the power in the cavity and jump between the energies. And when we run the sequence, we could see in time of flight panel, AVO Adam was written every 2 seconds. So here we have between every pulse, we were operating at 100 Hertz repetition rate here. So between every pulse, we have 10 milliseconds. Now, after we finished the feasibility study in Geneva, we started working on our first system in the UK. So this is a famous building in STFC. There was an electrostatic accelerator in the past here, and there was a free space in this building, and the company had some agreements with the Science Council in the UK, STFC. This is in Daresbury in the UK. And we are building our machine in this building here, and LINAC is right behind this tower in this direction. And here there is a transfer line. So LINAC transfer line, and we have our treatment room somewhere about here. At the moment, treatment room is being built, and we also installed the full LINAC. We will go a bit more detail, and next steps, we have the, first of all, commissioning of the full LINAC, beam commissioning very soon, and then we will have the habit installation and habit tests, high energy beam transport, and then we will have the tests of the we'll have medical tests for the beam and the verification. We have also, so this area is also dedicated to us, and we have our rack room here, and it's 2 floors here. We have clutch stones upstairs, and we have a round accelerator control room here. So status of the project in Daresbury. As of today, we installed all the accelerating structures. So what you see here, they're all installed with all their clutch stones and everything. And recently, we reached to 90 MeV in July 2022. So 90 MeV up to here, we had everything installed up to here, and we had the test bench for the beam measurements. We are performing measurements here. Once we conclude this, they installed all the other structures. These are showing the beam commissioning phases. We call them phases. You can call them steps or other things. So we did the source commissioning, RFQ commissioning, then several steps SDTL commissioning, and in few steps we have the CCL commissioning. Why do we need to have these phases? And if you look, we actually have more phases in the beginning of the accelerator. It's always challenging to have the to commission the lower energy part of the proton LINACs. This is where you form the beam, and this is where you define actually what the performance of the full LINAC will be. So we put a lot of care in this part, and so that we can go faster later. Well, now I want to talk about a little bit permanent diagnostic devices we have in this LINAC, so that you'll understand a little bit why we need those test benches. We have in the LINAC, between RFQ and SDTL, we have a mid-range beam transport. We call it MABIT1. And between the SDTL and the CCL, we had mid-range beam transport 2. And here in these 2 locations, we have steering magnets, AC current transformer from the beam current measurements. And also we have beam position monitors, but no other diagnostic devices for the beam measurements. And also in these locations, where I show, well, we also get a signal from the RFQ, but then we have beam measurement devices. They can be BPMs or they can be phase probes. We are taking signals from them, and we build what we call phase measurement system, and we can measure when the beam is arriving to each device, so that we can also measure time of flight between these 2 devices. For instance, if you switch on the machine up to here, but if you keep everything off here, the beam will just have a drift through these structures, and you can measure using 2 phase probes, you can measure time of flight. And this phase measurement system will be basically our eyes when we are monitoring the beam performance and also recommissioning the LINAC in the future. So main targets of the beam commissioning phases we had. When you perform beam commissioning, first of all, you want to optimize your machine and get the beam parameters right. And this is usually the longest part of the beam commissioning. Changing the machine parameters, for example, scanning the RF cavities, changing the steering magnets, trying to get the beam through and getting the energy right. And once you do this, you can start understanding your machine more. Here you can make dedicated beam measurements, and you can compare measurements and simulations. And you need to answer here you need to ask yourself if your cavities are working as they designed. So this is very important to answer, and this is the way to do it through simulations and measurement. We were thinking what we should do during the commissioning phases. So when you are in a research institute and in private company, the pressure might be quite different. So we were trying to do many things at a short time, but we wanted to do enough. And one important thing we said we will do, we will validate our strategy for the recommissioning of this machine because we don't have many diagnostic devices in this Linux. We need to make sure that we can recommission it and we can optimize the performance again. So we put a lot of effort on this. And we also performed regular daily machine QAs to monitor the performance of the machine every day, several times. And at the end, you can take some reference measurements to keep for future commissioning. You can measure the beam properties, or you can also measure some machine parameters. So this is basically the recipe we follow. Obviously, it's very open to interpretation when you start, because in the beam commissioning, you cannot really write a recipe and follow. You need to, sometimes you need to decide on the fly, depending on what you measure on this day. In terms of RFQ commissioning, well, maybe it's important to mention here, the first RFQ we commissioned in Geneva, it was built by CERN, designed by CERN, built by CERN. And this RFQ we are using in Daresbury, it was designed by CERN, but it was built in an Italian company. And we wanted to make sure that this RFQ will work also as the other one, and it worked. The industry, the Italian company made quite a good job producing it. And we had very good results also through this RFQ. It was basically giving more or less the same performance of the previous one. When you commission the RFQ, it's very, very important to measure this characteristic curve of transmission. You have this in simulation, and to define where you need to operate the RFQ, this is the measurement you do. You change the power in the RFQ, and you measure the transmission. And when you have the spectrometer magnet here, or some test bench here, you can just send the beam to spectrometer magnet and see what portion of the beam is accelerated, because this is what we are looking for. But if you don't have a spectrometer magnet after installation here, what device do you use? So this is another thing we want to answer. And what you see here in this figure is the measurement of this characteristic curve of transmission from two different devices and one simulation. In blue, you see the simulation. In red, you see measurement. Okay, it ends here, but you get this part here, which is the important part. It's measured here with the beam position monitor, and the green curve here is measured in spectrometer arm in the test bench. As you can see here, the result we get from the beam position monitor and spectrometer arm, they are matching quite well. This is why we decided to use beam position monitor in the future to get this characteristic curve of transmission of the RFQ. We also have an ACT here, and I will just briefly mention why we cannot use this ACT. Through the RFQ, depending on the input beam you put and depending on the energy you put in the RFQ, you might have some unaccelerated particles, and we want to measure only the accelerated particles. And if we measure this curve with the ACT, this is such a curve we measure. This is simulated and measurements. It's very difficult to simulate through the RFQ unaccelerated particles. So this is why these curves are not matching perfectly. But if you look here, this is 96% in the field level. And in this figure, it's about here. And as you can see, as we have zero transmission for the accelerated particles, 5 MeV particles, we still have quite a lot of particles at the low energy. So this is why the BPM was a better choice for this measurement in the future. And we did this measurement with BPMs several times during the commissioning phases, and it worked nicely every time. And this is the transverse emittance measurements after the RFQ we did in Daresbury, and it gave quite a good agreement with the simulations, what we measured and what we simulated. So ACDTL commissioning, after the RFQ, we installed different ACDTLs. So we didn't install all of them again. We went step by step, and these are the commissioning phases we followed. First, we put a test bench here before we installed these 3 cavities, and we measured the beam here. And then at this location and at the end of the ACDTLs. So we measured different beam parameters in all these commissioning phases. We measured beam intensity with Faraday cups and direct transverse emittance at this low energy. We used slits with Faraday cup method, which worked quite nicely. And we measured energy and time of flight, energy with time of flight and spectrometer, and transverse profiles and beam position. It's maybe important to mention here, I told you we have about 70 electromagnets in our machine. the SDTL section is quite low compared to quite short compared to CCLs, but it has more PMQs inside. So it has 40 PMQs. This short distance is about 40 PMQs, and we don't have any steering magnets here. So what we do is we motorized all our 70 PMQs, and we can control them. We can control the PMQ positions from the control room, and we can use also these PMQs for steering. By the way, a PMQ we have is about this size, this microphone. So they are quite tiny and easy to move around. A few results from the SDTL commissioning. When you do commissioning, it's very important to scan the machine parameters to maximize your beam performance. Just an example here, when we scan the steering magnets here, we have two sets of steering magnets in the medium energy beam transport. We were scanning the parameters to find the optimum transmission through the SDTL, and this is such a scan we perform, 2D scan usually, and you see some black dots here and then contour plots around. Each black dot here, it has, in this case, it is 10 pulse or 100. Yeah, it has 100 pulses measured. We take averaging and then we plot contour plots like this to see where the transmission is. And for this, we develop some automatic measurement application. Without this, it would be very, very long, this measurement. Another method we used, I will call this signature matching. Well, you can scan the machine parameters and you can measure different beam parameters, and you can measure signature of the structure on different beam parameters. In this case, I show you the transmission. On the left side, you see the simulated transmission through the SDTL module 1. When you scan the phase of the cavity and change the power in the cavity, voltage of the cavity. And this is we expected such a signature, and this is what we measured on the right side when you change the phase and amplitude of the cavity. I will not go through all the commissioning phases because it would take very long, but I want to mention one important thing, the validation of the recommissioning strategy. So when we installed all the SDTLs here, we had a test bench here, and we had a lot of devices here with time of flight and everything. We could measure and we could optimize the structures, and we can find their operating points with time of flight. And this is what you see on the left side, the signature matching for the energy. Simulated and measured curves matching quite well, and this would be our operating phase here. And we want to make sure that we can also use the phase measurements of system for this scanning and the signature matching. And we used only one device here from phase measurement system, a signal coming from the BPM, and we could also find the operating points of the cavity with only one signal coming from the BPM quite nicely, and this two agreed to each other within 0.5% in field and few degrees in phase, which was quite nice to see. So we actually convinced ourselves that we don't even need time of flight measurements in the LINAC to re-optimize the machine. We can only use phase information from phase measurement system and compare this with simulations with the signature matching method and find operating points. And here we also measured emittance just to show you how it looks like. This was quite important to measure. We actually measured everywhere. And this is showing us that the focusing channel here is working correctly with 40 permanent magnetic powder posts. SDTL commissioning. After we finished the CCL commissioning, SDTL commissioning finished here, and we installed 6 CCL modules, and we had a test bench here. What we did in this case, after quick reoptimization of this machine up to here, getting the beam to 37.5 MeV, and then we started switching on all these cavities one by one. Every time we switched on one, we did some scans, and we found their operating points, and we did this both with time of flight in the test bench, and with the 2 phase props we installed here, they will be permanent there. What you see here, okay, let's look at this one first. This is 54 MeV. That means we were scanning this cavity here, and when we scan the cavity face at certain amplitude, the energy changes like this at the through the machine here. And comparing the measurements and simulations, we could find the setting of the cavity where we need to operate. And this measurement is using only the phase probe information from here. And by using this phase probe information, we could also conclude the same thing. So we were doing such measurements both with test bench and also the permanent diagnostic devices to validate our strategy. And after switching on all these cavities one by one and scanning the last cavity, and this is how it looks like for the signature matching at 3 different amplitudes. And this is 90 MeV here, and this is about 88 MeV, and this is about 86 MeV. So if you lower the voltage of the cavity, you have less acceleration. And this is such a signature. This cavity leaves such a signature when you scan the face of the cavity, and comparing the simulations and measurements, we could find the operating points. And at the end of the 90 MeV commissioning, we reached up to 45 microamp beam current and like 90 MeV beam. And our target at the end of LINAC is about 40 microamp. Maybe it's important to mention one thing. You cannot spend like months and months to optimize the machine. Obviously, there is still room to optimize in this machine. As we are trying to get to the end of the machine, we can leave certain optimization to later. And this is again, optimization of the time of the project. So next steps, at the moment, we have all duct setting structures installed, and this is how it looks like now from the top view. The beam starts here, comes all the way here, and the test bench starts at this point. This is the magnets of the test bench. And these are the CCL structures here. You cannot even see the SCDTLs, they're down there. And this is basically the end of the machine. And this is a side view of the CCLs. They are all installed, and the waveguides are everything connected. At the moment, the component tests and the dry run, will start very soon, next week. And after dry run finishes, we will start the beam and we will get to 230 MeV. And next year, we will have the high energy beam transport commissioning, and already the medical room is being installed at the moment, and there'll be some medical tests in the medical control room, and afterwards, some patient treatment. Okay, I want to talk a little bit about the operation, but I believe I don't have time, so I will skip this, but we can discuss in person if you want later. Conclusion, in AVR we started in 2018. Well, in 2018, we demonstrated the 52 MeV acceleration through this LINAC, through 3 different structures. And we are building the first machine at the moment in the UK, and we installed the full LINAC at the moment, and we will start the beam commissioning very soon in a few weeks. And hopefully in 2023, we will have the heavy commissioning and connect the LINAC to the treatment room. And afterwards, the medical tests can start, and we will have the validation and verification to get the medical certificate. And then we will have the treatment, patient treatment in Daresbury. Okay, thank you very much.
Thank you. Thanks a lot again, Willy. So do we have any questions from the audience or Zoom? One question, 2 questions. Okay, we start with Professor Anna.
Hello. Could you remind me the transmission percentage of your RFQ, first of all?
Well, transmission really depends on what you inject to the structure. The design transmission of the RFQ is 30%, but if you inject what the beam that you use for the design, you will get 30%, but at the moment we have about 15 to 20% because our emittance coming from the ion source is larger than what it should be.
That means you will have a good number of unaccelerated particles. In your test bench, you have a dipole and you get rid of them. But yeah. In your intended setup, I didn't see a chicane or anything. What do you intend to do?
We have very strong quadrupole magnets. So I didn't mention, but our quadrupole magnets are really, really strong. They can go up to 200 Tesla per meter in gradient. And when these are unaccelerated particles pass through these quadrupole magnets, they basically hit the beam pipe. And they don't enter the next structures.
Okay, I understand. You work, that was my last question. You work with permanent quadrupoles. did you think of making permanent solenoid-like structures?
For the low energy beam transport. So low energy beam transport, we are actually using Einzel lenses. We don't use magnetic focusing in our Lebit. We didn't think about making permanent magnet solenoids, but we were discussing maybe we should make a permanent magnet dipole.
Thank you.
Okay, thank you for your nice talk. For 230 MeV proton linear, is it useful for medical purpose or the others?
So 230 MeV, with 230 MeV proton beam, you can go up to 30 centimeter depth in tissue. So we can treat up to 30 centimeter depth cancer, and by changing the energy, we can change this depth.
Okay, then
And that's enough.
The following up question is, in practice, 250 MeV cyclotron versus this LINAC, there's a pros, advantage and disadvantages.
Yeah.
Can you briefly compare that?
Yeah. I cannot go back. Okay, I will just verbally comment. So at the moment, there is only one commercial product being used for the proton therapy, and they are the cyclotrons. So cyclotrons, they are reliable machines, and they can have even maybe smaller footprints if you consider only the machine. But there is a huge shielding around it, and they cannot change the energy. So the energy from the energy from cyclotron is fixed. So the advantage of LINAC is you can just switch off the modulator klystron, or not sending the power to the last structures. You can immediately change the beam energy, and we can do this within 5 milliseconds. So we can jump from 70 MeV and 230 MeV within 5 milliseconds, and this is very, very advantageous.
Thank you very much.
May I ask a question?
There is one question in the room, Alessandra. Maybe after that.
Sorry.
Take yours.
Thanks for your talk. I see that the system you build in England is your own property, and it's your first commissioning to 230 soon. And is it a plan to hold the structure within your company and even not sell, but commercially operate it? That was my first point. Second is, when you commercialize and on demand, maybe prepare and sell to other places, do you also provide the necessary person power to operate such a structure to your customers, let's say?
Yeah. So this first machine we are building in Daresbury, we will keep it there for a while. We will have patient treatment there, but it's not clear at the moment how long we will keep it. But there are already plans to move this machine to to a hospital. I don't know all the details, but as far as I heard in the company, so there is what they plan to do. They plan to sell this machine to hospitals for a reasonable price, but with some agreements, get some of the profit from the treatment and get paid in a longer term, let's say. So give the machine not with the full price as a cheaper, but have kind of agreement with the hospitals and get some of the profit. And Daresbury is quite good for us because we are building our full machine there, and we are also learning how to maintain the machine and how to, we are learning how much manpower is needed to operate and maintain this machine. I couldn't mention, but we started building an operations team, for example, in Daresbury, and the operators are there from the beginning of the commissioning. We want to make sure that we can actually train people who can go to different sites and operate the machine there. And we are also building this manpower at the moment. there is still a lot to figure out, obviously, but slowly. Yeah, Alessandra, we can take your question as well.
Thank you, Veli, first of all, for the excellent talk and for the impressive work of all the team. I had a question a little bit going forward. Do you have any comments about availability, reliability, and preventative maintenance?
Which maintenance you said?
Let's say availability, reliability, and preventative maintenance. So maintenance that you will have during shutdown to increase or maintain your availability and reliability.
Yeah, well, we are in the company, we are building a strategy for this as well. Maintenance, when we can do maintenance, and we are working also with our suppliers to understand when is the good time to do this. In terms of reliability, it's very difficult to talk. We have been keeping we have been checking how much we can operate the beam per day. It was about 80%, but it's commissioning phase, as you know. We did not have time because we had some push from the management to go fast. We did not have time to run the machine for a longer period and understand how reliable it is. But this will hopefully come after building the full machine. I'm hoping we will have some time to answer this question as well, because I'm also curious.
Okay, thank you.
Welcome.
I have two questions. One of them is rather simple. It's just my ignorance about cyclotrons. The answer you gave about cyclotrons made me realize that I had not thought how they actually operate a cyclotron-based hadron therapy machine if you are unable to adjust beam energy. Is there something in the gantry that just degrades the beam, or I don't know? How do they do it then?
Can I connect my question with that question?
Just ask a question, so after that.
I'm connected to Ercan question. What is the advantages when you compare with the cyclotrons for the medical therapy? I mean, LINAC and cyclotrons.
Okay. Can you repeat the question? I didn't get it. Did you hear the question? Okay, so cyclotrons, you have, it's simpler in terms of operation. It's a solid body, you install it there, you have a small number of power supplies, we have a lot of klystrons. Beam losses would be higher in cyclotron, especially when you try to decrease the energy. In cyclotrons, they usually put an energy degrader. It's a metallic sheet, and depending on its thickness, when the beam passes through, it will reduce the energy, but there is a very, very large energy spread, and then you need to put, excuse me, you need to put an energy selection system afterwards with the magnets, and you will select the correct energy, but all the energies will be lost, and the performance is very low, and the radiation is quite high. And in our case, we can just switch off the machine as it's LINAC, it will just go straight. So that's the advantage. But in terms of operation of the cyclotron, it's quite simple.
Okay, and my second question is, do you have any business models where the company makes a research agreement with an institute? So for instance, instead of being a hospital that you sell it to, would you build something in which a research institute also learns something but still pays you for the device, etc.?
Difficult to answer, but so first, we were so busy with building this machine, all our focus was there, and we could not invest any time on this kind of collaborations, but we would be open for collaboration, I believe, in the future, and we can discuss, and when I go back, I can also discuss in the company. But I believe we would be open. Obviously, collaboration, if both sides are profiting from that, why not?
More questions? Let's thank our speaker again.
Thank you.
So, okay, we give a 20 minutes break. So let's see you in 20 minutes. So 11:20, Turkish time, 10:20, Southern Geneva time. Thank you.
Chasing that A and want to save time on proofreading? Grammarly makes editing one click simpler. We can suggest ways to
Can I ask you? Okay.
Welcome to the second session of the morning. So we have Nikolina Ilic from University of Toronto and CERN, as far as I remember. And she's going to talk about accelerating and decelerating neutrinos. So floor is yours, Nikolina.
Thank you very much. Right. So yeah, I'll tell you a little bit about how we make a neutrino beam. And my talk is not so much focused on acceleration or applications of accelerators, but I'll tell you about neutrino detection, which I hope that you'll find interesting as well. So I want to start off first with a bit of a physics motivation. So the idea is that Dune is going to be constructed and be online towards 2029. And its primary objective is going to be to try and answer some of the remaining mysteries related to neutrinos within the standard model. So namely, it's going to be sensitive to measuring the neutrino mass hierarchy. And here you can see the sensitivity as a function of the number of years running. So you can see that for all of regardless of the CP violating phase, after about 2 years of running, we'll have 5 sigma sensitivity to the mass ordering. And the CP violating phase is a bit more complicated after, if we're lucky and the CP violating phase is something simple, we'll have it after about 4 years, as you can see by the pink line. If for 50% of the values, we'll have 5 sigma sensitivity after about 6 years. And then if we're unlucky and the CP violating phase falls elsewhere, for 75% of the values, we'll have it after about 14 years. Dune is also going to be sort of a general purpose detector. So it's going to be sensitive to neutrinos coming from the sun, for example. So this is what the mass spectrum of neutrinos as a function of the energy from the sun looks like. So this is the boron-8 spectrum. This is the HEP spectrum. And you can see that we'll be able to detect it with a quite good efficiency as a function of the neutrino energy. If you look at the red line here, so there's about 97% efficiency. And if we add additional information from the photon detection system, it falls down a little bit. But one of the reasons that detecting solar neutrinos is interesting is because it'll not only help us verify the standard solar model, it'll help us characterize the neutrino floor. So dark matter experiments are approaching this floor here where neutrinos are going to become their dominant background. And you can see here, boron-8 neutrinos are going to be the first thing that dark matter experiments see. So characterizing this is going to be useful for them. We can learn things about the core temperature of the sun, as well as resolve some tensions in current experimental measurements. We can also detect neutrinos from supernova events. So, 2 to 3 times every 100 years, we expect a supernova to happen at a distance of 10 to 15 kiloparsecs from here. And these are going to be really low energy neutrinos, so about 10 MeV, but they're going to come to us at a flux over the course of about 10 seconds. So Dune is going to be able to hopefully detect them. And this is just a plot that shows supernova neutrinos as a function of time. If we had normal ordering, if we had no oscillations, it would be the blue. And then for inverted and normal ordering, it's the green and red respectively. So we can use these neutrinos to learn about astrophysical events, test again the mass ordering, and probe additional beyond standard model effects. And then Dune is going to be sensitive to a whole array of beyond standard model physics. I've included 2 interesting examples here, but there's a whole slew of them. So one interesting thing is the possibility of extra neutrinos that can exist. So this is interesting in terms of some anomalous measurements at other neutrino experiments that suggest maybe there's a 4th neutrino. So Dune, if you look at the mass coupling of the 4th neutrino to the standard model neutrinos as a function of the mass splitting as a function of the coupling, you can see the Dune sensitivity is in the black. Everything to the right of this curve is excluded. So you can see Dune will have quite good sensitivity for lower mass splittings. And then we'll be sensitive to more exotic things like dark matter, for example. So you can imagine if there's a dark matter particle interacting, it can scatter off the electron in the liquid argon. And then the coupling as a function of the mass of the dark matter limits are shown for Dune in the red here. And you can see it's quite competitive with dark matter experiments, even though it will not be a dark matter experiment. So now that I've hopefully motivated a little bit what Dune will be capable of doing, I'll tell you a little bit about how we make the neutrino beam and how we detect the subsequent neutrinos. So it's going to be a wide muon neutrino antineutrino energy, about 1 to 6 GeV. And it's going to be obtained from a high powered proton beam, which is going to start at 1.2 megawatts, but will be upgradable to 2.4 megawatts. So the idea is we're going to produce the neutrino beam using a proton accelerator at a Fermilab site here. Then after the neutrinos are produced, they're first going to pass through a near detector site, which is going to characterize the flux of the beam as well as measure the liquid argon interactions with neutrinos. And then the neutrinos are going to pass 1,300 kilometers underground to a mine in South Dakota at the Sanford Underground Facility, where we're going to have a far detector that's going to do a lot of the oscillation measurements. So now I'll tell you a little bit about each of these different components. First, starting, before I get to that, let me get about the manpower. Let me get to the manpower involved in the Dune collaboration. So we're over 1,400 collaborators, including Turkey, from over 200 institutions and more than 30 countries plus CERN. So in terms of manpower, it's quite a large project. So let me start off with how we make the neutrino beam. So it's similar actually to how we get neutrinos from the atmosphere. So typically, when you have a cosmic ray shower, you'll have a proton or something hitting the atmosphere, and then it'll decay to a pion or a kaon. And then you'll have the pions and kaons decay to muons and muon neutrinos. So that is the process that happens within the atmosphere. And we've basically copied that process and put it in our accelerator. So we first smash protons into a target, and then we focus them. We focus the resulting pions and kaons with a magnet, which are these focusing horns. Then we have a decay pipe in which we just allowed the pions and kaons to decay. They decay into muons and neutrinos. We shield the neutrinos, we stop them, and then the muon neutrino beam continues underground here to the far detector. So a few words on the accelerator. So again, this is located at Fermilab. So we're going to have this is the acceleration facility. It's going to start in PIP2, superconducting cryo module. So it's a new 250-meter accelerator. It has superconducting cavities that accelerate protons up to 800 MeV. So again, it's 1.2 megawatts of energy upgradable to multi-TV so that we can provide protons in the 60 to 120 GeV range, and this will enable the world's most intense neutrino beam. And then we have an additional booster that accelerates the particles to 8 GeV, and then the main ejector is going to accelerate them to 20 GeV. So this is the main part here, and then where you're going to hit it into the target here, and then the decay pub and the muon absorber. The main accelerator, this main pipeline, basically it's 79 conventional magnets, 25 dipoles, 21 quadrupoles, 6 kickers, so nothing too extravagant here. And the design and the site preparation for all this is already completed. So then moving on to the second part of the accelerator. So there's this, not the accelerator, these focusing horns. So these focusing horns, we're in the process of prototyping them. The idea is we're going to be able to switch them in order to select and focus particles with opposite charges. And what this will allow us to do will allow us to either select to run in neutrino or anti-neutrino mode. And by running in the two different modes, we can compare what effects we expect from the CP violating nature of the neutrinos and from the fact that neutrinos travel through the Earth from the matter effects. The target is a graphite cylinder, and there's some beam parameters here if you're interested. The beam size is 1 to 4 millimeters, and there's other parameters that I won't go over, but well, yeah, if you're interested, is there for reference. So then I'll start off with, after we produce this neutrino beam, they go to the near detector. So the near detector consists of actually 3 different types of technologies. The first one is a liquid argon TPC with a muon spectrometer surrounding it. It's very similar to the far detector, and it's going to be used to characterize the beam flux and neutrino interactions. So if the neutrinos are coming from this side here, this closest one is this liquid argon near detector. The second one is a gaseous argon detector. It's going to be the second module here, and it's surrounded by an ecal and a muon system in a magnetic field, and it's going to have very good tracking resolution in order to be able to study low momentum neutrino and liquid argon interactions. And finally, we're going to have SAND, a system for on-axis neutrino detection, which is the end detector here. It's an inner tracker, ecal, and magnet field that basically serve as the beam monitor and measure neutrino interactions. And one interesting thing about this near detector is these first two components, the liquid and gaseous liquid argon, they can move in and out of the beam. So if the beam is coming from this direction, it'll be able to measure the beam from this axis, but also from other angles. And the idea of measuring the beam at different angles is that we'll be able to characterize the beam flux at different energies effectively. So this, for example, this is the beam. If you have an on-axis beam, so if the position is here, you can measure it over a wide range of energies. And if you have it far off axis, you can measure the fluxes in narrow energy bands. So now I'll move on to the far detector. After the beam is characterized in the near detector, it travels to the far detector. And the far detector consists of four, basically 17 kiloton modules. So if you imagine a neutrino beam coming from this direction here, we'll have one module here, the second one here, third and fourth. And this is 1.5 kilometers underground. So the first module is what we call a single phase liquid argon time projection chamber. So it's split into 4 different drift volumes. And if you zoom into how one of those, if you zoom into what happens in one of these drift volumes, what you see is you have the cathode planes on one side. You have 3 anode wires oriented at different angles to each other on the other side. So when a neutrino interacts in the liquid argon, it ionizes it. The free electrons move toward the wires, and from that we can reconstruct these 2D images. Liquid argon is also a really good scintillator, which means that a lot of photons are going to be released, and we have a photon detection system that collects the photons right away, and it's going to give us an immediate time of when this interaction happened, which is useful because these electrons will take a while to drift to the wires. This design, what we call horizontal drift, allows for a 3.5 meter drift region in an electric field of about 500 volts per centimeter. Again, zooming in a little bit on what one of these actually looks like. So these wires that I mentioned are built on what we called anode plane assembly. So if we zoom in here, we see this is an anode plane assembly unit interspaced with photon detection systems. And if we zoom to the top part of that, you can see the 3 different wires that I mentioned in the purple, green, and blue oriented at different angles that will detect the electrons. The signal will be read out on front readout boards up here. And the front end readout boards are going to digitalize and do the analog to digital conversion and amplify the signal, and then send it outside of the cryostat to these T-shaped structures. And the T-shaped structures contain what we call warm interface boards, which are basically going to put the signal into 10 gigabyte optical fibers for transfer onto the data acquisition system later on. So each of these parts has been prototyped. So starting with the drift region in big detectors at the neutrino platform at CERN. So if we zoom in on one of these drift region, this is that anode plane assembly. You can see the different wires oriented at different angles in the copper here. The front end boards that read it out, you can see at the end here. This is a zoom in of the front end board. And then outside the cryostat, these T-shaped structures I mentioned are here that house these warm interface boards, and then read out with DAC. The data acquisition system I haven't talked a lot about, but it's a high performance input output computing system. The detector input is 1.5 terabytes per second at a rate, and data rate to tape has to be maintained below 30 petabytes per year. So we have to reduce it by quite a bit. It's an FPGA based readout. So the data comes from the detector. It's read out on FPGA based boards and then sent basically to commercial computers for the event building, triggering, and so on. One challenge of the data acquisition system is receiving the supernova events. So the supernova events, again, are going to happen over the course of 10 seconds. So in order to look for these supernova events, the data acquisition system has to be constantly buffering data to make sure that we don't throw any of it out, decide what's a supernova event, and then decide to retain it. So as I mentioned, all the things are prototypes, and this is the neutrino platform at CERN where they all sit. So this is the single phase detector. It ran between 2018 and 2020, and it showed excellent performance. It had 99% of electronics responsive, 99% high voltage uptime. This is an example of an event display. You can see this is a 6 GeV electron. You can see the very fine features in different particle tracks, which means that it had excellent resolution. The detector performed really well. And currently this is being revamped in order to prototype the vertical drift design, which I will describe in the following slides. So the vertical drift design, the idea is it's going to be used in the second module. And why we're going to a different design is because this design is going to be cheaper and it's going to basically need less material to install. The installation is also going to be simplified. And this is because with the vertical drift design, instead of having a 3.6 drift volume, we're actually allowed to have a 6.5 meter drift volume. So here you can see the cathode is in the middle. We're going to read out the charges on the top and the bottom, and it allows for a larger drift volume with equal resolutions. And a bit of a lower E field of 450 volts per centimeter. So zooming into one of these readout planes. So the readout is not going to happen on wires. It's actually going to happen on charge readout plates, which are double-sided perforated PCBs basically. And then the data is going to be sent in what we call signal feed-through chimneys, which are pipes that penetrate the cryostat. So the bottom is warm, the bottom is cold, the top is warm. And because of that, we have to fill them with ultra-high vacuum. They have to be maintained at ultra-high vacuum. So after they go through the pipes, they basically go into micro TCA crates, which house these what we call AMC cards that do the signal amplification, digitalization, and so on. And then they're converted to a White Rabbit network switch and transferred to DAC. So these components for the second module are also all prototypes. So starting with the drift chambers to the pipes, you can see the top part of the warm signal feed-throughs and the bottom part of the cold front-end electronics. And then the micro TCA cards housing the AMC, micro TCA crates housing the AMC cards. All of these, again, are installed in the neutrino platform at CERN, and hopefully later on in the fall, we will test this design. So as a summary, I forgot to include a bullet point about the accelerator, but the acceleration neutrino part, it's designed and is underway. Things have been excavated, and there's a lot of prototyping on more novel components of the system, like the magnet horns. The experiment, DUNE, is going to be a broad energy range experiment. It's going to receive the highest neutrino intensities beam provided by the Fermilab accelerators. It will have unprecedented sensitivity to the neutrino mass hierarchy. It'll have good sensitivity to CP violation, searches for extra neutrinos, atmospheric neutrinos, supernova neutrinos, a wide beyond standard model physics program. The TDRs were completed for both the accelerators and the experiments. The fire detector construction and near construction are both underway, and hopefully the fire detector will take data in the late 2020s with the neutrino beam expected on a similar timescale. Thank you.
So do we have any questions from audience or Zoom?
This is a very nice experiment. I was wondering how you get ready for the, first of all, how often do you supernova events in your detector?
So at a distance of about 10 to 15 kiloparsecs from Earth, we expect them 2 to 3 times every 100 years. So once, maybe twice in the lifetime of the experiment.
Okay, so then comes my next question. How do you get ready for that sort of thing? I mean,
so we don't get ready for it. We're always, so this is one of the challenges with the data acquisition system that I described. We're always saving all of the data. We're buffering it on SSDs. And then we're analyzing on the fly in the readout servers to see if it's a potential supernova event. So there's always 10 to 100 seconds of buffer data. And once it's decided it's a supernova event, we save it. So you can imagine 40 kilotons of buffer data in the readout on SSDs is quite the challenge. And we're in the process right now of purchasing, like, I don't know, $55,000 servers to try and see if these can handle that challenge.
Okay, so this I understand, but it's also quite interesting, right? Because you don't know how to calibrate for it, or how do you, I mean.
It's quite a specific signal. There's not much else that can, it makes the whole detector light up at low energy. So it's a high flux of 10 MeV neutrinos. So we expect all 40 kilotons to just light up over the course of 10 seconds, roughly the range of 10 MeV or so. So it's a bit of a specific signal. Yeah. Calibration, I mean, we know what we expect it to look like from simulation, but there's nothing else that we can think of from the beam or the atmosphere that would provide, the lighting up of the whole detector.
Okay. Yeah, I think it's still a challenge. I mean, for an ordinary in quotes detector on an accelerator, on a collider, you can calibrate, or well, you can just get ready by using cosmics or something like that. For this sort of thing, you expect this very rarely, and once it is there, you have to make sure that you haven't missed it in some way. So it is beautiful work.
Yes, it's true. And one thing that I didn't also note is we're going to be integrated with SNOOS. So it's this multi-messenger astronomy system that's going to be included, from photon, from gamma ray experiments, telescopes, other neutrino experiments like IceCube. So what's in the development is an entire system of this multi-messenger astronomy that we're going to be integrated with. So if, for example, IceCube detects higher energy neutrinos slightly before us, or if we, from other experiments, see gamma ray bursts, for example, we're going to roughly know to be prepared. Vice versa, if we see our detector light up first, we're going to, via the SNOOS system, tell them to be prepared or to look in a certain direction. Because one of the other things we're working on development is once we notice the detector light up, the possibility to tell us what direction the light is coming from. So these directionality studies using various machine learning algorithms, we hope will also, if we see the signal first, tell other telescopes, okay, point there, look there, and so on.
Thank you.
Do we have any more questions? Yes.
Well, I would like to ask a question about what you mentioned in terms of dark matter. So dark matter, dark energy, are you planning to install any cavity-like structures like ADMX stuff in the far end, in the dune mine?
Sorry, there was a lot of static. I understood the question was about dark matter and whether the far detector will be able to detect it. Was that the question?
Can you repeat?
No, my question was, are you planning or intending to install something like ADMX cavities for dark matter detection in the dune mine experimental area?
So the question was whether we're planning to install something for dark matter detection, but I didn't get what that something was.
ADMX. ADMX.
Right. No, but we do have other ideas. So one of the things that we're hoping to do is to dope the liquid argon with various materials that we're exploring in order to make it sensitive to various to lower wavelengths. Another thing that I didn't mention is, so the third and fourth module, especially the fourth module, is very ill-defined right now. It's basically, there's no design for it currently. And we're calling it the module of opportunity because we're hoping we can make this one very sensitive to dark matter things, for example. And it doesn't even have to be a liquid argon TPC. So basically anything that dark matter experiments can do, we can also borrow for this fourth module of opportunity. For the first two modules, the only other possibilities that we can do is this doping I described, but for the third and fourth modules, there's all sorts of opportunities for different designs that will make us more sensitive to dark matter. I hope that answers the question.
The question from audience? No? Okay, if there is no more questions or comments, let's thank our speaker again. So now we continue with Professor Ömer İldan from Bilkent University, and he's going to talk about how an accelerator technology and a science fiction idea to let ultra efficient laser micro machining. So Professor İldan, you can share your screen and start as you like.
Hello. So thank you for the introduction and for the invitation. Can you confirm that you can hear me well?
You and see you.
Sorry, come again?
We can see you and hear you.
Excellent. All right. So once again, thank you for the invitation. This is a somewhat an off-topic talk, which I'm giving essentially in praise of interdisciplinary research, because it's really, as the title announces, a bit of a story of how an idea I learned from accelerated technology helped us realize an idea that came out of science fiction and to make it real, which is having a lot of impact on laser material interactions and in particular laser micro machining and surgery. So I think everyone has at some level heard of laser material processing. In fact, it's by far the biggest application for high power lasers, particularly outside of the research laboratory. It's also probably the earliest application of lasers. Here you see a paper published in 1961 by one of the inventors of the laser, Gordon Gould, already drawing attention to the physiological implication of laser beams. And in fact, just 2 years later, the first laser surgery advance was realized and published. Now it's actually a huge area.
Excuse me, Ömer Hoca, excuse me. So your screen is not changing. Can you share the other screen if you have? Because we got stuck in the first slide.
Huh, that's funny. All right. I mean, I have no other screen. How about now?
No. We just see a strip line of thumbnails.
I don't understand. It's not the first time I'm giving a talk over Zoom. Never had this problem.
If you like, you can restart your Zoom. We can wait 2 minutes if you like. It is not.
Well, I think they did an update with Zoom. If you just start the presentation first, then go share your Zoom whatever screen, and then want to go to full screen, it doesn't work. So what you have to do is you need to go first to full screen and then share the full screen desktop onto us. I had the same problem 2 days ago.
That's strange because I always do this like so. You know, I lectured for 2 years with Zoom.
But while you trying, it was turning. Few seconds.
How about now?
Can you change the?
I'm doing it. It's not changing. Yes. Oh, it is changing. It's just late.
It works. So sorry.
Okay, so apologies for the interruption. I was trying, I thought I was showing this slide. This is the paper by Gordon Gould from '61, talking about physiological applications of laser beams, which led to the development of laser surgery, the first example of which came in 1963. And in parallel, regular processing of materials first in the automotive industry came within a few years later. And today, this is a major application, in particular, so-called ultra-fast lasers, lasers that produce pulses that are in the femtosecond duration, are exalted for their ultra-high precision. In particular, basically all of us have smartphones and the glasses of these phones are cut with these lasers. Not only that, a lot of high-end applications that require precision use this technology. And this is known as a very successful method, praised in hundreds and thousands of papers, which, by the way, begs the question, if ultra-fast lasers are so great, why are these lasers a niche in the marketplace of high-power lasers? They constitute less than 1% of the total number of high-power lasers out there. The reason is that as great as ultra-fast lasers are, they're expensive, slow, and very inefficient. And this talk explains how we solved the slow and inefficient aspects of these problems with an idea that came from science fiction. But before I get to it, I'll show you another historical reference, because I think popular media is a mirror of the reception of scientific ideas in the population at large. And this is actually a scene from my favorite Bond movie, Goldfinger, in which the villain is threatening to cut Mr. Bond in half using a laser, which during the movie is going through what appears to be a steel plate at a fairly high speed of tens of centimeters in less than a minute. Now, at the time in 1964, this was science fiction. Today, we have lasers that are this fast, but if you use such a laser, you would be hitting the steel plate so much, all of it, that you'd be actually cooking Mr. Bond before you would actually start cutting him. Something like this is only possible with an ultra-fast laser because it localizes the energy delivery within a few microns of the laser beam's location. But if you used such a laser, I calculated it would take about 100 years to cut Mr. Bond in half. So these lasers are indeed slow and inefficient. And the reason is, well, we can blame the Beer-Lambert law, which describes how electromagnetic radiation is absorbed in a material in an exponential fashion. So if the 0 point here represents the surface of your material, as you go deeper into the material, the amount of light absorbed decreases exponentially. And the process of ablation, which is an explosive removal of the material with ultrafast pulses, occurs basically if you're above a threshold in the absorbed energy. We can take this threshold to be infinitely sharp for the purpose of this talk, which would imply that if you actually deliver this amount of energy, if this is the threshold, you'll ablate material all the way down to this depth. But the rest of the material that absorbed this energy would simply stay put. You would have delivered substantial amount of heat here, and you would have ablated some of the material. And if you try to fit a rectangle into an exponential, you see that you have a tough choice. You can keep the ablation threshold low or high. Either way, you have a chunk of energy here and a chunk of energy here that is not contributing to ablation. And in fact, the chunk that is here is causing heating of the material. Even though all you needed was to deliver this amount of energy to ablate, you have ended up putting substantial heat down here. That's going to diffuse into the bulk of the material. But actually, you have to then wait for the heat to sufficiently diffuse away before you send the next pulse. Otherwise, even while using femtosecond pulses, you can have terrible heat effects on tissue or other thermally sensitive materials. So at a low repetition rate, maybe this works brilliantly. If you try to increase the repetition rate, therefore the speed of the process, you get into trouble. This is why you're inefficient and you're very slow. And for decades, people assumed that we simply have to limit ourselves to low repetition rates in the kilohertz range. Well, we said we'll take a different perspective, and we asked, what happens if you go the opposite way? We send the pulses so quickly that we not only not wait for the heat to diffuse away, but we send them so fast that there is no time for the heat to diffuse away at all. Here's the geometric justification of this idea. When you focus a laser beam on a surface and you're ablating the material, you're creating a local plasma, which is absorbing almost like a metal, regardless of the linear optical properties of the material. And this absorbing layer is very thin, less than a micron, typically tens of microns wide. So between the time this energy is absorbed and before the next pulse comes in. Initially, the diffusion of heat is essentially like a plane way out of this very thin wafer into the bulk of the material. So the material is ablated and heat is diffusing. Now, if you hit it with another pulse, very shortly afterwards, within picoseconds, you basically catch all of the heat within the same volume that you're going to target and hopefully ablate with your next pulse. You ablate that and then you send one other pulse, one after another, always catching up with your heat. Now let's go back to the Beer-Lambert picture to see the implication. We are sending low energy pulses, each of them ablating a tiny amount of material, but we send the next one before the heat left over by the previous pulse can diffuse away. This does two things. First, you're recycling the leftover heat. It doesn't diffuse into the environment. You simply utilize it to reduce the amount of energy you need to send because you're already finding a very hot material as a target. And second, you're actually removing the heat away from the surface, not by letting it diffuse away, but essentially by ablation. The heat is leaving the surface trapped inside the material that you're exploding away. And you get something much closer to the ideal of this rectangular area. Now, where is the term ablation cooling coming from? Well, actually, I developed the idea independently, but shortly before we submitted the paper, at which time it didn't have this title, I was reading this book, Ring World by Niven. I'm a science fiction fan. And in it, I read the following passage that says, a meteorite can be cooled by ablation by the boiling away of its own skin. This gave me the idea. I immediately, this was 2 a.m., I got up and Wikipedia'd it and noticed and learned that actually this is an idea that's commonly used in rocket science to protect any spacecraft that re-enters the atmosphere. So in fact, very interestingly enough, it turns out that the idea came into rocket science from an early science fiction book published in 1934. So it appears to be the case that this idea made it from science fiction to science independently twice. Now, there was one other problem, and this is where the accelerators came into the picture. This idea required that we went from tens to maybe 100 kilohertz repetition rates to many, many gigahertz repetition rates. At the time, this was simply impossible in terms of the laser technology involved because we needed certain pulse energies. Microjoules at multi-gigahertz means that you need kilowatts of average powers. This was absolutely impossible in 2011 for femtosecond pulses. Even today, it's basically not possible. So how to do that? The idea came because I had prior experience contributing to accelerators. I was the person to propose and demonstrate the first optical timing and synchronization scheme together with a colleague, Axel Winter from DAISY, which got adopted eventually, and I believe it's now the mechanism used at EuroXFEL as well as a few other accelerators worldwide. This experience introduced me to the technology and physics of accelerators, from where I was familiarized with the concept of forming micro bunches out of your electron beams. And I decided to duplicate the idea here. The implication and implementation in the case of the lasers is depicted by this image, which shows a group of optical pulses that we generate from the laser. And then we stop the laser's emission only to repeat this group that we call bursts in the laser community. Now, the advantage is that within this burst, you can have your hard pulse energies and as high repetitions at rates as you would need. But by changing the time delay between the subsequent bursts, we control the duty cycle of the pulses, therefore the actual average power we would need. And with this idea, we were able to develop the relevant lasers, the necessary laser technology that allowed us to get to multi-gigahertz repetition rates and microjoule energies without requiring kilowatts of average power. In fact, the first demonstrations were with several watts of average power. Now, with this capability, with this technology developed, we were able to demonstrate one by one all the key findings of or key claims of the ablation cooling idea. I'll show several of them here. One is that by increasing the repetition rates, we could go to much lower pulse energies while at the same time having much higher efficiencies. Lower pulse energies simplifies the laser technology and helps its adaptation. More importantly, prior to this, because of the Bird-Lambert law, the amount of ablated material scaled logarithmically with the incident pulse energy. But with this method, it scales linearly. The more energy you want, the more pulses you put into your burst. And in fact, we've had record high efficiencies. In fact, even with a single burst, we can make extremely efficient and deep cuts into virtually any material, including biological tissues such as brain tissue, dentine tissue. This is results from human dentine. We have even superseded our own record by a factor of almost another order of magnitude. Here you're seeing us doing this in real time, cleaning rotten teeth, decayed teeth. We've applied this to corneal flap removal in ophthalmology. And here you can see us cutting a piece of glass with this laser. Now, this is actually emerging as a universal tool that can be applied from anything from metals to silicon to tooth to brain or glass. And this is actually having a big impact now. Virtually all ultra-fast laser manufacturers are offering lasers with burst mode operation to harness these benefits. To sum up, I've just briefly talked about a new physical regime of laser material removal. This is a new regime because unlike all previous cases, the main mechanism of the laser's energy leaving the premises isn't diffusion into the bulk, but it's getting carried away by ablated material. It gives you greater speeds and far, far higher efficiencies. This is a technique we've proven on a vast variety of different materials. And we increased efficiencies by roughly a factor of 100 in these different materials. And I believe the longest term impact will be in laser surgery because now we are reaching speeds that are medically relevant. It also allowed us to reduce pulse energies by more than a factor of 1,000, which I think is going to lead to the development of a new generation of lasers that are far simpler and probably lower cost than the existing ones. And all of this came because, well, I think partly because I was familiar with accelerator technology. So thank you, fellow accelerator scientists. So I'll be happy to take any questions if you have.
Thanks a lot, Professor Eli, for a very interesting talk. So do we have any questions or comments to Professor Eli from audience or from Zoom?
I think someone raised a hand on Zoom.
Okay, please, on Zoom, can you go ahead?
Yeah, thank you for such a nice talk. It's the second time I listened to you, and it was again so interesting. Do you think it is possible to also use for tumor therapy?
So for what?
Ablation of the tumors.
Absolutely, that's my vision. Absolutely. In fact, I want to put these pulses into optical fibers. The pulse energy reduction allows us to transfer these beams in optical fibers without damaging the fiber or without distorting the pulses. And I want to put these fibers into micro needles and stick it deep inside the human body to reach inaccessible tumors. That's absolutely what I want to do, but give me a decade for that.
Very, very great and interesting idea. I hope application comes soon to help the cancer patients. Thank you.
Thank you. It will require cooperation with medical imaging scientists because we need to see where the tumor is as we reach towards it with this needle concept.
Sure, yeah. Thank you.
Thank you.
there is no more question, so we can thank Professor Ilday again.
Thank you.
So now we have Eric Montesinos from CERN. He's going to talk about something very, very useful for our accelerator community, RF power generators. Has he connected?
Yep, I am.
Yep. Okay, we can see you. You can share your screen, Eric, and you can start anytime you like.
Thank you very much. Just trying to put it full screen. Okay, got it. So, hello everybody. I'm Eric Montesinos from CERN, working on RF power sources and main power couplers since more than 30 years. I really want to thank you for inviting me for this talk, and I want to apologize for not being with you in person. I would have loved to be there, but my schedule does not allow to do that. So I try to put all about RF powering for accelerators on some slides, and let us go through that. But first thing I want to say is that RF powering for us means going from watt to kilowatt and to megawatt, and everybody has to keep in mind it means for going from money to a lot of money and to a very lot of money. And this is very important for all projects because people have the tendency to believe that we can buy that off the shelf. It's a bit more complex than that. So a quick outlook, I will go to the RF power amplifiers for accelerator, then a bit of RF power lines. This is important. You will see a single slide on FPC, fundamental power couplers, and quite some slide on efficiency as well, because this is a topic that is more and more important. RF power amplifier means it's only the triangle that you have on many of the block diagrams. And this is made by various items that could be vacuum tubes with three main families that are the grid tubes, the linear beam tubes, or the crossed field tubes. And the second big family are the transistors, with a long list of transistors that we use in accelerators since a lot of time. I will start with the triode and tetrodes very, very quickly on the basics, and just to keep you to have in mind that it started in 1904, so more than a century ago, and within the first few 10, 20 years, a lot has been done, and then we're using the same concepts since that time. Only, let's say 70 years later, we had a big diacrode that has been designed, and this is linked to the fact that finally, this is the technology that is blocking and not the theory. But it's very difficult to braze all these ceramics onto the collar rings and with the high power system that you have there. So the concept is essentially to have a vacuum tube, to have a cathode with thermionic emission and electron cloud. Then you put an anode, and then you have the electrons flying and you have a current. This is the concept of diode. Then if you reverse the voltage, you do not have current flying, and that's the diode. Then you put a first grid, and then you have a triode, and you have a bit of acceleration and amplification, but there are some limitations because you have this parasitic pseudo in between the anode and the grid, and because of that, there is a tendency to oscillate. So what they did, they added a second grid, that is the screen grid, in order to decouple the anode from the grid one and to increase a bit the gain. The limitation there is that we have a secondary emission of electrons coming from the anode and flying back to the screen grid. And that's the reason why these anodes are treated to reduce the secondary emission. And this is a bit the specialty of the tube suppliers. If you look at the concept, this is always the same. You have the tetrode, and you can have a RF in within the cathode and the grid one, and you can have the grounded grid system. You can have the cathode grid system, but basically this is the same since decades. And the systems looks like this. So you have the big tubes, and you immediately understand that with high power, you have a cooling system. These are the red pipes that have to be decoupled from the high voltage. So you put this tube inside a trolley, and you have all the connections for the grid systems around, and then you can have plenty of these tubes connected together in order to have the maximum power. So where do we stand today with the tetrodes and diacrodes available from industry? So I try to make you a plot in order for you to think about your project. The blue triangles mean continuous wave, and you see that for lower frequency, we're above a megawatt. But if you increase the frequency, the power reduces pretty quickly, and almost the maximum one we have is 450 megahertz with half or 50 kilowatt. On peak power, this is almost the same. The frequency is reducing the power, and you have less and less when you are increasing the frequency. Now, if we move a bit to the klystrons, so the concept is a bit different, but again, as almost 1 century ago now, as well as the IoTs, in fact, they have been developed almost the same time, but the klystron got much more use in the accelerators than the IoTs. Nevertheless, we had pretty soon the multi-megawatt klystrons, and it has been quite long to have the high efficiency IoTs. So the principle is really different. This is a velocity modulation of the thermionic cathode that you have there. Then you put the anode, you accelerate, you have a beam of electrons flying back to the collectors. And then if you put input cavity, you have the puncher, then you collect at the output cavity, the catcher, what you have. And to do so, you inject a bit of RF, this accelerates some electrons, some are decelerated, and finally you bunch the electrons to have the maximum density at the catcher cavity. Another way to look at it is this diagram where you apply the RF along time, and you see that the neutral electrons are flying along. The ones that are accelerated are coming at the same time at the output cavity, and the red ones that are decelerated, they are coming also at the same time at the output cavity. And this is the goal of a klystron. To increase a bit the gain of a klystron, you have additional cavities that helps to have more power, and in order to keep the beam where you want and exactly at the output cavity, you have all the magnets around. So what we have that is a bit top of the heart nowadays is these kind of klystrons that you have in the LHC. They are already, let's say, 15 years old, but still they are a very good one. You can see all along quite a lot of magnets that are to focus them, and we have plenty of cavities there. We have 7 cavities in order to increase the gain of the system. This is in operation since 2008, and we have plenty of them all around the same group. So these are all the klystrons that you have available from the industry, and as you can see, the frequency is in the lower frequency, we are almost the same power as the triode, but if you increase the frequency, you can have still klystrons that you do not have with the grid tubes. And on the peak power, you can reach really high values that we have for these kind of frequency, 3 gigahertz. And even if you go to 12 gigahertz, you still have some klystrons that are very, very powerful. But pulse power and average power is very low in that case. My preferred one is the inductive output tube, that is the IoT. This is a mix between a tetrode, where you have this grid system modulating the electrons and making the bunching with the grid and not with the velocity. And then you have an acceleration and the output catcher. The advantage of this one is the gain is in between the tetrode and the klystrons, but it's very nice to have this modulation given by the grid because you can do all kind of exercise you wish with it. This is what we recently put in operation. Recently means less than 10 years in operation at CERN. These are Thales klystrons that you combine all together. So you have four IoTs combined together through a 3dB combining system, and a second set of 4 IoTs combined together. This is very useful in order to increase the power and to make a lot of gymnastic with the ref. The next generation that we worked out, that is, we had some results only a few years ago, is the multi-beam IoTs. So it was a collaboration with ESS in order to check if ESS could go for multi-beam IoTs. And we had a collaboration with Thales CPI, and we reached 1.35 megawatt peak with 5% duty cycle and 750 megahertz. And again, we had a collaboration with L3, and we also had 1.2 megawatt peak with a collaboration with the L3, as I said, and ESS colleagues, Morten Jensen here. So where do we stand with the IoTs? This has been less requested for accelerators. This is a bit of pity because we can do what you want from, let's say, lower frequencies. We do not have dots here because nobody requested that, but we can do it. And we have even up to 1.3 gigahertz IoTs that are available. And in peak power, it's a bit more. in the sense that these beautiful IoTs, if the collector is big enough, you can go up to CW with the same system. And the new one are the transistors that are coming into accelerators since, let's say, 15 years. And the history of that is, let's say that the theory has been made at the beginning of last century, but technically speaking, it was not easy to build it up. So it came a bit later onto the market, almost at the same time or a bit later than the klystrons. This is what it would look like in the past, of course. And now we all have this kind of modules or this kind of chip in our systems. The principle we mainly use is to have this push-pull system with two different devices. So the balloon has been invented such that you rotate one of the fraction of the signal, and then you rotate a second time such that you use the same kind of devices in the same chip, which helps a lot in the construction of it. This is a kind of plate you can have with the two transistors here, so twice a pair. You have the balloon system that you can witness here, and then you combine and you have a full power. Here, notice that the plot is to show you that it's linked to watt and not kilowatts. So we can go to 1 kilowatt, let's say, with the lower frequencies. And if you increase the frequency up to 2.5 gigahertz, you have a few fraction of watt, and it's difficult to go higher. And here only CW, because CW or pulse for the transistors is almost the same business. This is linked to the cooling system of the transistors. For the transistor, what is even more important than for the tube is the combining system. So first of all, you can go for a very simple combiner with two amplifiers combined together. This is a resistive system that can do the job. But if you want to go for high power, you have to go for hybrid combiners, splitters, and combiners, because if not, the loads will have too many limitations and you cannot increase the power. So with a simple 3dB combiner, if you play correctly with the phase and the gain that you can play with a simple phase shifter and attenuator in front of the amplifier, you have this simple formula that says that everything is going to the output with twice the power and nothing is going to the delta, that is the last part of the combiner. If you want to go to high power, you have this kind of combiner. So you can see that it takes quite a lot of place. This is huge combiners with big lines going at lower frequency. Here we're talking 200 megahertz, so it takes a bit of space. But here you can inject 100 kilowatts, and then you can go to the megawatt level at the output. Another way is to use the low loss T junctions. This is what Soleil has decided to do for the amplifier. And then you can build the N-ways splitters, and here you have the trick to play with that. This is what they did in order to have the solid state, the first big solid state tower. So one tower here is 45 kilowatt, 352 megahertz. They did that in 2004 and an upgrade in 2007. And then a bit later on, you had ESRF that did the same kind of principle, but going higher in power, sticking to the same frequency. Then we try to improve the system for the solid state. And for the solid state, what is very interesting to do is to go from the 3dB combiner that I've just explained to the cavity combiner. And the cavity combiner is this kind of things where you have plenty of input into one output in a single stage. And here we succeeded to have 144 times 1 kilowatt to 1 time 144 kilowatt. And if you go even further, you can do this very high power cavity combiner. And here we connected 16 times 70 kilowatt to have 1 time 1 megawatt. And if you compare these two systems, they're used for the same kind of amplifier. You need 50 square meter and you need 3 square meter to obtain the same power output. And this is the scheme of how it works. Another advantage of such a combining system is that if you go for a 3dB combiner and you want to have a degraded output of, let's say, 12 base units, you need 16 units, because if you have 2 modules failing or 2 tetrodes failing, then if you apply all the formula, you will see that you need 16 to have 12. If you go with the cavity combiner system to have 12 base units at the end, you need only 14, because the cavity combiner is direct. It's not linked to some losses you have in the various loads you have in the system. So this is really useful. Another main advantage of this cavity combiner is that if you go for lower modules, and then you have one module that is grouped with a single power supply for tubes, for example, then unfortunately you will lose more tubes, and then you need more tubes to have only that example. I put 9 base unit just to show the real differences with grouped or common power supplies, you lose a lot. Then with the cavity combiner, you lose much less. So this is a pretty young technology, the solid state. But if you use all this trick with the cavity combiners and all the modules that are individual, ensuring the granularity, you have this kind of very beautiful system that is in operation since only last year. So it's a very recent one. And I can tell you it's impressive because the availability for BIM has been 100% over the last 2 years, despite we had a lot of problem with the systems, thanks to the granularity. So if you now go for the transistor available from industry and you group them by 100 of transistors to make a tower, for example, this time you move to kilowatt instead of being a watt, and you compete with the other power sources. Now, what we can expect in the coming years, if you look at what Soleil did in 2004, what ASRF did in 2012, and what we did at CERN in 2021, you see the power density has considerably increased. Of course, we have to be careful because we're not comparing the same frequencies. So what I did is a kind of plot of what has been done in 2004 with respect to various frequencies and extrapolation to what could be done for the future. And typically for the FCC, we're looking at 400 megahertz and 800 megahertz. And these are the power densities that we need for FCC that will be in 2040 or above. And this is what we already succeeded to do. And if you look at the trend, we should be able to do that within the next 10 years. Just a few numbers to situate the solid state amplifiers in the accelerators. These are the number of transistors that has been sold for the mobile phone over time worldwide. And you can see that last end of centuries, it was almost nothing. And within the last 30 years, that's been incredibly increasing. And if you translate that in the market size in billion US dollar, you can see that within the last, oh, sorry, the plot is not correct, but it's only in the last 6 years, you will see that it has also doubled, almost doubled in a few time. Another point to notice is that you have quite a lot of key players in the solid state business, as you have much less key players now in the tubes technology. To notice that probably LDMOS is what has been used by most of the accelerators within the last few years, but the new technologies are getting up, and probably this is a perspective that has been made in 27. Probably LDMOS will let the place to gas and GaN. This has to be seen with respect to the various frequencies that we will use in the future. There is nevertheless a drawback with the solid state that you have to be aware. This is what we call the overhead comparison. In fact, if you took the blue line, these are the tetrodes. If you normalize the input power versus the nominal input power compared to the output power, nominal output power, you want to operate that point. With the tetrode, if you overdrive by factor 2 or 3 or even 4, you still have output power and no destruction of anything. With the klystrons, you have the saturation that is sitting here, and usually we try to operate the klystron 30, 25% lower than the saturation, because if not, the low-level RF gets completely crazy. And with the solid state, you have to be careful. I stopped the line here because it's normally the 1 dB compression point, but if you go above, you can even destroy your transistors. So you have to be careful to very correctly protect the transistors in order not to destroy them. So the system has to be really perfectly designed. I also try to summarize a bit in that plot what are the different implications of the choice you can make. If you use a tetrode, you have 15 kilovolt, the klystron 100 kilovolt, IoT is in between 40 kilovolt, and solid state is not using kilovolt but only volts. So this could be useful depending on the qualification of the personnel you have in the various systems. The driver, because of the gain, is pretty high with the tetrode, nothing with the klystron, mid with the IoTs, and absolutely nothing with the solid state themselves. And then here you have the kind of combiner you would need in order to reach 1 megawatt with the various technology. So you can see that you have to take into consideration some losses that you can have with the flange on the combiners. The trend is to transistor. This is absolutely visible. However, for some applications, tubes are still the best option. And I tried to summarize the number of talks by category of tube that we had at the CWRF workshops with the 10 years interval. And if you look at this in the 2012, we had a bit of graded tube talks. We had quite some klystrons, and we had solid state growing up. If you look at 2022, the conference will be next week. We will have almost nothing on graded tubes, you have still klystrons, because some of the applications, as I said, are still with the klystrons, and you will have a lot of solid state. Everybody is slightly moving to solid state. Okay, apart from the source itself, what is really important are the RF power lines. So I try to summarize a bit, because you have the rectangular waveguide. This is well-known technology, but you have to take it into consideration for the integration into the machine. And this is all normalized. You have the various sizes, but you also have to keep in mind that there is a frequency range, and the peak power is given by the size of the waveguide as well. So this is limiting a bit what you can use. For the attenuation, the big one are less attenuating, of course, and this is the reason why we can use them at lower frequencies, but if you go higher in frequencies, more attenuation. The coaxial line is also something that you do not have to neglect, because when you have to connect a big amplifier to your cavity, you need big lines, and it's not a little cable like this, but a big line like this one, and you see the inner line compared to the outer line. This is really, really big. This one is a 14 inches one, used for 200 megahertz. And there you also have the maximum power handling that I summarized here. Keep in mind that the flat line per color means the maximum peak power. You can lower the frequency, but you cannot reach higher power. And the end of each line is what you can expect to have as a frequency with the coax line. So you can see that 1 gigahertz is almost a kind of limitation. And attenuation in the lines depends mainly on what you have in the line. So if you have air, alumina, or PTFE, you will have additional losses that you have also to take into consideration. Okay, very quickly, if you have reflection from the loads, unfortunately, you can have destruction of your system. And this is very important for the transistor system, that you have to keep in mind that with full reflection, you can have twice the voltage coming back or flying back to the transistor, which is an immediate destruction, or you can have opposite phase twice the current. And this is not immediate destruction, but it could be quickly a destruction of the transistor as well. So in case of full reflection, an option not to have the circulator, I will talk about just after, is to have a very quick protection that is quick enough such that the system is not destroyed. This is something we use with the tetrode, and we use with the IoT very successfully. The one I shown for the SPS transistors, we do not have circulator, but a quick protection. Most of the klystrons, they request to have a circulator not to disturb the catcher cavity. So the circulator is a very magic item that you have the full reflection or the wave going to the device in the test, and full reflection coming back. This is well known, but I just want to underline with this slide is normally you have this line that is a pretty small one, because you need to sustain only the voltage forward. But this one has to be bigger, because you have to sustain forward and reverse. And I've seen so many projects where this line has been undersized, the output line has been undersized, and then there was some destruction because the reverse voltage was added to the forward voltage, and there was some arcing in the line making some destruction. So in case of full reflection, you have to think about power as well, because it could be current, and then the maximum power equivalent of the line has to be 4 times the forward power. This is also something that can make some destruction in the systems, and that's the reason why the circulator should stand, if you want to make your system less expensive, as close as possible to your cavity or device under test, because the output line is normally bigger than the input line. Just that slide on fundamental power couplers. This is not part of the RF power generation, but this is in the line, and this is a very specific device with a ceramic window ensuring the insulation between beam vacuum and the feeding line. You have to be careful. This one takes 2 to 5 years to be designed and constructed. So this item should be thought from the very beginning as well. Of course, overall efficiency is directly linked to electrical bill. This is an old slide, but still, again, when you look at all the documents that we receive, I always hear about this klystron is 90% efficient, 85% efficient, etc. This is true for RF power in versus RF power out. But a system is much more complex than that. You will have to take into consideration your AC power in with the conversion AC to DC. You have to take into consideration, and this is reducing a lot the efficiency, how to get the heat out. And for this, you have an amplifier cooler. and this amplifier cooler and the amplifier are sitting inside the building, and then you need a building cooler. And these two, one on the top, building cooler and amplifier cooler, are very, very bad for efficiency, and they drop down to 45% almost for all the systems. So a few tricks to try to increase the efficiency is to take this system you have on the surface building, the 32 towers that I shown you, transistor amplifier, very beautiful. And then you have a long, long line of 150 meters going to the cavities that are down, I don't know if you see my mouse, but down on the machine with the traveling wave cavities. So I made a kind of example, 1 megawatt, and I looked at all the things that we can work out in order to increase the efficiency. So first of all, the design report said that the efficiency of the RF block is in the order of 66%. This is a conservative value. For this exercise, I took 60% just to be sure that we take into consideration bandwidth adjustment, linearity, etc., etc. So we go from 1 megawatt to only 41.9% efficiency, overall efficiency, when you take everything into consideration. Now, one single trick is, instead of having your amplifiers 150 meters away from your cavity, try to put the amplifier very close to the cavity. And this is the reason why we said, okay, we want to have the gallery for the HL-LHC. That is perhaps very expensive, but we have to put it close to the cavity in order to reduce the losses and to increase the operational efficiency. And then you can save 4% there. Then try to make a system that is circulator free. This will help to reduce a bit the losses by, let's say, 5 to 5%. And then you increase the frequency, the efficiency global from 42% to 45%. Now try to go for cavity combiner or radial combiner instead of the old 3 dB combiners with the loads. This will also help to reduce the number of flanges, and the number of flanges will help to reduce the overall losses and then increase the efficiency. And we gain here more than 6% total. Then the granularity is also a solution that allows to switch on only what is needed and not to have this overhead that is in operation. And then you can switch on only what you need, what you really need. This helps to increase the DC to RF efficiency as well as the AC to DC efficiency. And if you look at that, we can increase from 42% to 55%. And finally, try to be innovative with the way you are doing your cooling of the system. Here for this building, we try to make something a bit innovative by taking the fresh air for the outside, pulsing inside towers and getting it outside and not cooling down the same air all the time. And this helps to reduce as well the losses. And as you can see, without any technological change, you can go from 42% to more than 58%, which is really, really important. Then one of my final slides, just to show you acquisition and operation costs, because everybody is moving to solid state, but then why don't we simply go to solid state and nothing else? The answer is a bit in this table. If you look at the technology, including the solid state driver, because I believe even the tetrode now you will have a solid state driver. You have the very rough estimates for 100 kilowatt continuous wave, 352 megahertz system. This was a choice to try to make this cost for such a system. And you see that there is indeed a difference in the acquisition cost between the tetrodes and the solid state. And this is based on the markets we did over the last 5 years. Now the lifetime is the expected one. I just want to mention as well that you need high voltage specialists for the maintenance of the system. That could have also a little cost. And if you go for 20 years of maintenance, we calculated the cost, and these are the difference. The solid state needs much less than the tetrode. And if you go for the electrical bill, and here my costs are really, really optimistic. This is why we have my contract for the next 2 years at CERN, but this will increase by a factor 10 probably. So this one will wait a lot, but somehow the technology, if you agree that the efficiency is dominated by the cooling system and additional system except the tube, will be almost the same. And at the end of the table, you see that the total cost for 20 years of operation will be almost the same independent to the technology. And this is probably the reason why not everybody is moving immediately to solid state, but you have to look what is the best for your system. So in conclusion, we plan to launch, or we even already launched R&D on combining system, because we believe this is the most important for the coming years in order to help the the various solid states topology to be available. We want to think about availability, including the granularity with the hot swappable modules and embedded spares. This is important. Hot swappable is an option. Embedded spare is another one that I've seen in various new projects that is really, really interesting. It means that you do not swap the module. You just have more modules in the system. And when one breaks, you put another one in operation pretty quickly, without any intervention and stop of the machine. This helps to have the availability of the machine. Of course, the next parameter is the efficiency, and it must be grid AC to RF for fair comparison, not only the RF power source. We have to work the low-cost circulators because at small power in the order of kilowatt, but also at high power in the order of megawatt, and we have to minimize the cost of this one, and especially for the transistors if you wish to have multi-circulators. Of course, you have to work out your cost optimization, asking for the correct architecture. So I mean by that the redundancy of the value system, as I tried to explain with the 3dB combiner compared to the cavity combiner, has to be looked at carefully because it could cost a lot of tubes. And of course, the mass production optimization, be careful that asking for more is not necessarily obtaining less cost. It could be the opposite event because companies will have to build additional premises and this could have a cost. So it's really asking the correct parameters and not oversizing just for safety and for nothing. And then we have to make a close follow-up of the new technologies available in large series production in the coming years, silicon carbide, gallium nitride, and 2D transistors, etc., because this is a very, very quick market, moving very, very quickly. Thank you very much. This was a quick overview. I just give you 3 links in order to go, and you see that this is almost 500 pages every time to talk about an RF power systems. The reference I took are coming from these books for all the formulas, and of course online you have Thales, C2B, CPI, i3Com, and Toshiba for the tubes, and these are the last one. And some of the pictures I took are coming from NXP and Freescale. Thank you very much.
So thanks a lot, Eric, for the very informative talk. So thanks again. So do we have any questions from audience? Oh, okay. Can you pass the microphone to Professor Runa?
Hello. Thank you for this great review. Diodes used to be a great option for pulsed power requirements, but it seems that the research somehow stopped, and maybe even they don't manufacture anymore. And Thales, being sort of monopoly in this business, makes it difficult. Could you comment on this?
Okay, you're perfectly right. As the tube market is decreasing, the other suppliers have not decided to move to diodes. Only Thales is doing it. But I will not say that diodes are not built anymore. As I know, I will meet with John Lights from Los Alamos in November, and they are doing the recipe of their new diodes for Los Alamos. This is not necessarily pulse mode. They are doing pulse mode, but we can also use that in continuous wave. But you're right, it is true that there is only Thales that has decided to move to this market. Diode is a beautiful tube, powering a lot of power with a single tube. So it's a single stage having a lot of power, a single supplier. What else can I say? Yes, this is a bit risky, but if you have good relationship with your supplier, in principle, it should last quite a decade or even more. We have contract with Thales that they guaranteed us to produce tubes for the next 10 years, and the lifetime is expected to be 5 to 10 years. So it's 20 years lifetime project. Okay. I love diodes. So.
Thank you very much.
So, do we have any other questions from audience or Zoom? I want to ask you something actually, Eric. So for the FCC, like big projects, we assume the klystron efficiency of 75%. Is it a little bit challenging, or is it like can be
So
provided?
it's challenging, but we have a program that we call high efficiency klystrons that is ongoing, that is led by Igor Sirachev. And for the first results we had, we can say that the simulations have demonstrated to be almost correct. They used a tube that was only 42% efficient. They calculated that the tube could be improved to 57% efficiency, and they succeeded to have 52. So we are almost there. And the point that we are not moving immediately to a new tube is the cost. It's very costly to have such a klystron constructed. So we try to go by step. And it seems that the 75% efficiency, but again, be careful, this is the efficiency DC to RF. This is not efficiency AC plug to RF that we're talking about. 75% efficiency seems to be something feasible. We are also working out to have the overhead that is a bit reduced. Instead of taking 30%, 1 dB overhead, we are looking at trying to reduce that value such that we do not construct an high efficiency klystron for 1 megawatt and then we will use it 750 kilowatt. We want to be closer to the saturation effect. So both together, the 75% efficiency DC to RF seems to be a correct target.
Okay, thanks a lot.
Just to mention on FCC, we're also working out multi-beam IoTs as an alternative to klystrons and solid state. It's surprising, but we can imagine to have 1 million solid state in the machine to do the job as well. Okay, let us dream about science fiction as the previous talk.
Okay. Thanks a lot, Eric. So we can, if there is no more questions, so we can thank our speaker again. So thanks a lot, Eric.
Thank you very much.
So now we have the last talk of the conference. It is for most of us, he was our RF engineering teacher at European Scientific Institute of Joint University Accelerator School. So he is a legend at CERN, again, like Eric, Fritz Kaspers, and he's going to talk about, I think, electromagnetic compatibility effects. So Fritz, once you are ready, you can share your screen and start.
Okay, I will try. So here we go. And just a second. I will get it on full screen. Move it up a bit. So here we are. Yeah, I really thank you for this invitation, and I have to say that this talk was essentially given already some years ago. And you see other names. You see the name Daniel Valuch and my name and Fred Schonzo. Like Fred Schonzo, myself, I'm also retired. And I'm still active, as you can see. And I warn you, we have 106 slides, more than 100 slides. And it gives you an overview. And this was the intention. Nobody who is a newcomer can understand everything, but the idea behind this is to give, a review, exchange experience, and give some guidelines and rules. And I hope I'm not going to stress your patience too much. So I'm starting. And so what is special at CERN? So we have internal limits, and of course I don't need to read it. And CERN has 100 groups of its own, user groups, and CERN is a big factory. And this talk will cover the things. And as I was myself one of the EMC policemen, and I did lots of stuff myself, and now we have real big commissariat. It's not only a policeman, it's a commissariat, where we have something like 25 people. And the borderline between experiments and machines is sometimes quite funny and tricky. And well, I will give you this overview. I'm sure there will be questions. And also, if you're interested for your own machine, to ask questions, to give comments, sooner or later, everybody is hit by EMI, electromagnetic interference, or EMC, electromagnetic compatibility problems. And it's usually much cheaper to tackle them in the beginning than fix them later. So this, nobody can really see, well, maybe. So this is a little bit our structure. So we have dedicated persons, EMC policemen. We have to comply with the European EMC standards, and which is sometimes a bit tricky because we are on the borderline between two countries. We have to really make sure that we get the proper shielding, proper earthing, and the selection of cables. We have the former IS-22, which gives, you see the word toxicity, which has had several revisions, and everybody building a new machine is advised to download these latest cable rules and to use them. So this is for the power converter group. And as you see, we have millions of highly sensitive measurement channels. We need an economic solution, and we get everything working peacefully together from power converter to RF systems. And then we have the big CERN divide, physics and electrical engineering. We have lots of customers, which are our physics experiments. And I remember situations where when I had this function of the EMC policeman, of course, like every policeman, he should help, not only chase and judge. And the people from the experiments were coming and saying, you're perturbing the experiment, you're making a lot of emissions. And then usually my first question was, well, emissions is one thing. How about your immunity? And immunity, what is this? The basic rule is to stay with the emissions within the rules, to have a safety gap, and then have your immunity. Otherwise, you cannot assure the peaceful living together of all this stuff. So we do have internal limits, and we have to keep in mind, like every big machine, that we are generating noise ourselves. There are some exceptions, no noise other than CERN's homemade, and they're even absorbing noise 100 meters underground. We had only one case, which we will discuss later. Then we had a very funny perturbation from the trains of the French Federal Railways. And so we do make noise ourselves, including from the beam. And we have to get this compatibility even with exotic services. And so it's not only that we have to stick to the European EMI EMC rules, which are big books of 10,000 of pages, but we have sometimes to get a little bit sharper rules. So this is also another important aspect. We should not pollute the environment. Here you see a nice Linux structure, which is not really underground. It is practically on the surface, and we must make sure that at the fence of CERN, and this includes a half sphere, which goes half over CERN, the emission rules are maintained. And there was a story, something like 25 years ago, or maybe longer, that we had pretty strong emissions from the PS at 114 megahertz. And then we got an angry message from the airport saying, this is exactly at the frequency of the landing system. And, you know, Geneva can be foggy, and it's not good if a jumbo would land in CERN and not on the runway. You know, CERN as runway is not that far away. And this was a nasty problem. And immediately there was a committee to find the source, and that was not easy. So this was beam-produced noise, and there are all kinds of leaks, and this has to be kept in mind. We have lots of machines. We have also to think, CERN, we have the proton synchrotron, which is more than 60 years old. We have magnets connected in series, and they are ramped up and down. And in the old days, we had a private power line to a private, in quotation mark, generator at a water barrage, because when you ramp up and down such a machine every 2 seconds, you get a flicker all over the place. So there are 30, 40 megawatts reactive going in, going out, and this gives a flicker all over the place, and we have to compensate this. Otherwise, people would be very angry with us, and it's also in our own interest. And here, such a machinery, there is the phase control for the SPS. And so we have to compensate things. We have to be as clean as possible in our own interest. And we have, once again, to make sure that all these high power units together with high sensitivity units are peacefully working together. And we are talking about big numbers. And 150 megavolt reactive is quite a lot to be compensated. And well, the LHC is a superconducting machine, and there's a lot of energy stored in the magnets. And you remember the accident we had a couple of years ago when one of these splices were behaving like a fuse, and all this energy was liberated in an uncontrolled way. And that was a major problem. And we have to keep this in mind. We have to supervise this and make sure that even under these very exotic conditions, we can control it and assure the peaceful living together, in particular when we get picker pulses. And of course, we have to avoid ripple on the beam, and that's what we have. So it's a real big task. These are typical frequency limits. dB microwatt, maybe not everybody is familiar with this unit, and we have to stay within these units. But sometimes we have even to be more stringent, and this is a story about the power converters. And usually these EMI, EMC rules for conducted emission start at 10 kilohertz. And so the company who made some power converters was quite clever and made it at 9.8 kilohertz or so. And so they were out of the rules, but this did modulate our beam, and it took quite some time to fix this. And we have internal limits also for the physics experiment, where for physics experiment, it's usually a unique device. It's not mass produced like in car industry. And what can go wrong will go wrong. And there are many groups, no common approach. These are our customers. And we have to make sure that within the possibilities, the immunity is good enough, the grounding, the shielding, and all this. And this is the main problem at CERN. And for most of you, you can always take a little bit slice of this big cake and use it in your own environment or on machine builder. And please do keep in mind when you're making a new machine, it's very important to have a sound EMI, EMC design, because fixing an EMI, EMC problem later costs you at least 10 times more than doing it properly in the beginning. Of course, testing. We have an immunity testing lab, the EMC lab, and here you see a situation where one unit is being tested, and okay, we can generate pretty high fields to test immunity. And there's screened rooms, and come to the next one, because I have a big number of slides, and of course, far too little time. The HERA experiment, typical configuration of a large experiment, how the grounding is done. And you have seen the word CBN, Common Bonding Network. Such an experiment consists of thousands, millions of units, sometimes very high sensitivity, and the proper grounding is quite important, and there are limitations. Sometimes you can use screens, sometimes not, and it's a real complex job. And sometimes these EMI, EMC relevant points are not accessible, and sensors can be floating, and there's all the philosophy how to do it properly. And usually physicists are doing it wrong in the first go. And it's always good to give them a hand, an experienced guy, to tell them, well, better don't do it this way. This mistake we made already 30 years ago. Let's make new mistakes. And you know the rule. Who works makes mistakes. Who works a lot makes many mistakes. Who makes no mistakes gets a promotion. And so this is a complicated learning process. And what you typically see on a spectrum analyzer is this kind of noise behavior. And then comes the question, what to do? And noise threats are ELF, it's not shown here, common mode and a random path. You never know where it comes from. RF background, digital signals, everything all over the place. Earth is not necessarily Earth. There can be certain potential difference. There can be big currents going over it. And there are ways to get around. but it's a pretty complex thing. And of course, I'm talking about CERN here. You are usually involved with smaller machines, but the lessons we learned, painfully in many cases, I try to pass on. Equipotentiality, there are rules, and putting everything on equipotential by just connecting things to the ground is one way, but one has to be careful. One should not create ground loops because any time-dependent magnetic field will create problems with these ground loops. There are rules. IEC, International Electrotechnical Commission, has many papers. I'm also a member in one of these subcommissions, and they're doing a lot of work, but in some cases they are not covering everything. However, one is legally required, at least what is going on outside, to respect these rules. And for CERN, the problem is the physical size. And when you have a smaller machine, things are easier. But with a machine of 28, or even if you want 50 kilometers of tunnels, it is complicated. Just a little reminder on grounding, when you say you put one point to ground at one location and another point somewhere else, keep in mind that the ground is not a perfect conductor. It goes over many orders of magnitude, and you see the average soil is 10 to 3 ohm meter, and the copper is 10 to -8. So there are 10, 11 orders of magnitude difference. And when you have a normal grounding, in our case, it's even more difficult because we have a calcaire, which is not the best conductor. Metallic grounding can be better. Cabling, cables, connectors. This is a typical cause of problem. So there are cable mechanics, parallel cabling, cable screens. There are typical mistakes, what not to do with cables. And so this is a typical way how a cable tray looks like. You have a tray, and there are lots of cables together. And by the way, just a reminder, this tray, which is usually made from zinc-plated stainless steel, gives also some magnetic shielding. And this shielding, especially when it is covered, can be quite useful against low-frequency electromagnetic perturbations. And I've seen where people use the aluminum trays. Yes, but aluminum is not magnetic. And in a worst case, it can burn. Steel doesn't really burn. And so there are a couple of rules. Improve the electromagnetic properties by not bending the cables too strong. Avoid connectors making a strong turn. And if you really need to do it, give it a 90-degree bend. More physical separation of signal and power. So try to avoid having your signal lines, even when they're digital, next to power lines, or at least give it a mild separation. And what is bad is reeling, sharp bends, what I said already, and squashing. We had this many times that some crew puts the cables in place, and then the questions, they were often like hooligans, and then we got all sort of leakage. And disconnected screens, this can happen. So these are just hints what not to do. And wide area loops. So cables always leak. And this is a quite important slide, because here you see the behavior of the shielding of the transfer impedance of several cables. And when you have a single mesh, okay, you get a moderate shielding. And we had very special cases. Look at the, I didn't just see, maybe you can see it. The pointer, the cable type number 7, which is a triple mesh plus a double mu metal layer. So usually at low frequencies below 1 megahertz, the cables with the mesh are not really, don't have the best shielding, and you need magnetic shielding, and that's what you do with the mu metal layer. And here we get an overview, and we use such cables in particular cases where we didn't find any other way around. So once we have a given cable, geometrical configurations determines everything, and here's an overview do proper grounding and shielding and everything. And below 1 megahertz, currents induced by ground loops dominate. And the shield is not really a shield. Keep in mind that at 1 megahertz, the skin depth in copper is 64 micron. And if you have a braid, it's even worse. And you should have several skin depths. Geometric cables, twisted pair, should have equal impedances to grounds. This is in particular relevant for experiments, not so much for people who construct the machines, but we did have some talks on experiments. And so I'm talking for both parties. And as I'm talking way too fast, it's just to give you a taste and later to have the capability to find back the slide, which is of interest. And here we come to a typical coaxial cable. We have the outer conductor, we have a jacket, a shield, insulation. We have triaxial cables. Triaxial cables do have advantages, in particular when you have to measure very small currents in high voltage environment. For instance, some electrostatic pickup or whatever it is, where you really have to have an isolation of teraohm, and with a normal cable you can't do that. So triaxial cables are good, but of course also more complicated, and you must carefully select, and this is also referring to experiments where they often uses. In the accelerator itself, it's less often used, but still quite important. The BNC connector is about the worst you can get. So it is useful, but it's by no means really very well leak tight. If you can avoid it, it's good. And if you get EMI, EMC from BNC connectors, don't be surprised. And other connectors are much better, N, or for smaller cables, SMA, but CBNC is really not the Daniel Cree. And when we have triaxial cables, we have to think about common mode to differential mode conversion and different impedance, characteristic impedances between the screen and the in and outer system. And bounded or isolated, it's all a philosophy in its own. And these are just some overviews, what to do and how to use it, what not to do, how to connect it. And as I said it already, this has been mainly used in experiments, which do have usually more EMI, EMC problems than the machine guys. But it's one of the rules which should be kept in mind. And as I said it already, this is a big collection of do's and don'ts, because even if you could digest all these 5,000 pages of EMI, EMC rules, you have to have it in your fingers and in your head. And it's very good to have these examples somewhere at hand. So, yeah, EMC guarded is more immune. So one of the biggest perturbers are the switch mode power supplies. I mentioned it already for the LHC. And when you're on the right frequency on a transverse tune, you know the revolution frequency in the SPS, in the LHC is 11 kilohertz. And when you hit the tune, even a very small signal can lead to a beam blow up, and this you really don't want. So again, we have a big experiment, point versus plane, and there's no time to explain all the details, but basically it's a compromise. You have somewhere one reference point which is reasonably clean, and then a common bonding network. So you have more modules which have their grounding, and this you do in a reasonable way. You see it here, 1 point and avoid loops. And yeah, so here we're coming to the photomultiplier, which is of less interest. So I quickly will click through because the talk is very long and we would have like some time for discussion. And no apparent CBN. Common bonding networks. This is an important thing. And the next important thing is a functional Earth. Do not build by accident a functional Earth. And I will explain in a moment what a functional Earth is. And here we have a nice example about the AD. the AD is a crowded experimental hall. And in terms of EMI/EMC, it is a disaster because it has been grown over the years and more customers, which means experimentalists came in. This is for the moment the only source of a significant amount of antiprotons in the world, and antimatter, antihydrogen, and it's totally crowded and not really easy. And so it has been growing and is growing much longer than it was originally planned. And there are metallic cable trays, I mentioned already. A metallic cable tray, in particular from stainless steel, is quite useful. And local ground planes as much as shielding as possible. This is a big physical detector. And once again, CERN can only give hints to the physics experiments. And here's a list of hints: common bonding network, DC powering, and separate screens, and all this what is written here. Examples of EMI/EMC solutions. The UA1, you remember all UA1, the famous experiment where the W and Z were found. And my colleague Sconso started his career, and he was bold enough to tell his big bosses that they make a mistake. So as the first go, he didn't get the job. So there are also psychological problems. Sometimes when the big boss says, this is all crap, I know what it is, and the young guy comes and knows it better, but doesn't tell it in the most diplomatic way, it can be difficult. So here we are as a Nobel Prize experiment. There was a lot of noise, and Sconso, who was a big part of this talk, made his career and helping people, and after a short time he was really respected. And this is a typical thing. One has to be the hunting dog, the chasing dog, find all this mess and to tell it to people in a gentle way, be the helpful policeman, not the punishing policeman. There are all sort of histories. One important thing, transistor data can change with radio frequency exposure. If they see it's a nonlinear effect, they don't have the same characteristics. And again, noise in the old stories, UA1, and I go through rather quickly because time is running, and I'm looking at my watch. So NA48 charge parity relation experiment, also the problem of proper grounding, proper signal transmission, and they did all kind of unprofessional measures against the noise. And where noise I don't really like, because noise for me is something which is thermal noise or comes from an amplifier. I personally prefer the word perturbation and or parasitics, but everybody uses noise. This is a particular nice one, magnetic field interference in the AD. So this is a highly sensitive antimatter experiment. And what finally happened in the end, it took a while to find it out. We have a crane in this hall, like everybody has, and this crane is moving around, and it's made of steel, and it's magnetized steel, and it did have a perturbation of this very, very sensitive antimatter experiment. So as an EMI/EMC officer, you have to have a lot of imagination, fantasy, and a good knowledge of Maxwell's theory, and always to anticipate what can go wrong will go wrong. CMS, 30 millitesla French field, heated and induction motor, and another nasty problem. So when you have a static French field and a squirrel cage motor, it doesn't like it. And pixel detector, DC-DC converters, also EMC trouble, and cooling and cabling for DC-DC converters. Sometimes you have a very low voltage and it picks up things. And here we have a slide about millions of CCDs are powered with 2.5 volt DC. And you can imagine when you have a 2.5 volt powering line, it is quite nasty when it picks up any noise. And radiation are DC-DC converters. Okay. Filters is always good. in-house commercial version, yeah, noise comparison, we do check things in-house sometimes. This is also a golden rule. Do not believe everything what the supplier is promising. In some cases, do make a check. Either it's the premises of the supplier or in-house when you have a record lab. And minimizing RF radiation. Yeah, we have a scanning table and we have a directional diagram. And we do these tests here. And especially for preamplifiers. And so this is a typical way to test things, and we have these problems all over the place, and we have to find a solution. So it's a friendly policeman, and get everything here are the typical measures to make some shielding, to put ferrite rings around, or to help the users to make a construction which really is safe. So we are discovering all sort of funny physics properties. For instance, the capacitance of certain capacitors is a function of the DC bias. Now it can happen. And then the filters don't work as they should work. SMD filters and okay, this can happen as a function of DC bias, and then the filter is not as good as it should be. So they can resonate, they can make all sorts of strange things, and that has to be taken into account. A series resonance of a 10 microfarad capacitor. Many people believe that when you put a big capacitor in parallel to something, everything is blocked. But these capacitors usually have their own resonances. And here comes the surprise. And slow discovery of the real problem in our EMC lab. And so here you see all tracks, sort of tracks, much detailed, measuring, absorbing after ionization. This can also lead to changes. Powering physics apparatus. Most EMC problems in physics result from remote powering. And when you have a long cable, this cable can pick up anything. So you have to be very careful about this kind of cable. All sort of loops, intentionally and unintentionally. Also linear power supplies can convey noise. And this was an example of something that switch mode power supplies are particularly bad, and common mode generation can be a real problem. And of course, leakage. And here are typical measurement traces where we make improvements. Switch mode power supplies from different makers. Parametric coupling, a sensor where it shouldn't be. For instance, the fluorescent lights from the ceiling make funny, it's a neon tube. As you see it, it's not really neon, it's a fluorescent tube coupling into a preamplifier, protecting diodes, which were not really shielded against the modulated optical thing from these fluorescent tubes. So it's a whole collection. The functional earth, and now I've got 5 or 7 minutes left. EMC applications, the hump. We see it when we look at our beam spectrum. And first attempt to move this possible common mode is low pass filter, but it didn't work well. This is a real funny one, and so I show it in a little bit more quietly. As you can see on the slide, we have the lab rings. That was in the times of lab, and we had a train which is powered by DC, 3000 volt or so. And strange enough, there were no perturbations on the tune in a certain period at night. And finally, after a lot of search, people found out that the intensity of the magnetic field was strongly correlated with the ground current going to ground from this power line or from the grounded rails of the train, which was DC powered. And DC powered means there are a couple of 100 amps or even more going into the ground, and they're going all over the way, 3, 4, 5 kilometers, find a very good conductor, which was a cell accelerator, and then finally end up in the Lake of Geneva. So functional earth. What is functional earth? Functional earth is an earth connection where some other current, which has a function, goes over it. And when you have earthing, one should usually avoid it. And So functional earthing is dangerous, and this was essentially, there's one exception. It is used for trains. This is a functional earth because the earth carries a lot of ground, which is a return current to the locomotion. And many people build functional earth by coincidence, and this is one of the classical mistakes. Our functional earth, yes, we have it. For instance, everything at Fern is grounded. And when we have a big kicker pulse, which is unipolar, we do get this return pulse all over the place. And people are thinking about how to change this in the future. But for the moment, the kicker bang, the kicker transient is seen all over the place. Here you see it. And there are many kiloamps, and even with the best contacts, you can't really get rid of it. Transients, screened cables, open earth connections, this happened over and over again. And laser ion source, it was delivered from Moscow, and it was in a terrible state. And some people even said it was so noisy that it could have been measured from a satellite. And there were all sort of tricks we had to apply to make it clean. So especially when you get things from Russia, be careful about EMI, EMC. At least 10 or 20 years ago, they were not very vigilant on this. And this was the story about the laser ion source. And everything had to be redone. And was not the radiation pattern from the laser optically, it was EMI, EMC, RF, and microwave radiation pattern. And we have many power devices, and we have all sort of cables, and also have an access system which does a scan of the iris, and it was perturbed by certain cell phones, and we had to get it. Here you see the mobile telephone was sending packets, and this perturbs the system. And well, I made it in time. Despite 106 slides, we are coming to the conclusions. CERN is a big beast. And you see all these accelerators here on one slide. And if you want to do EMI, EMC business with CERN, just as any engineer, a profound understanding of the systems is required. And the credo or the message is everybody designing hardware systems should be aware of EMI, EMC. And in every research lab, there should be a sort of EMI, EMC, policeman, officer, or whatever you may call it. And sometimes you have to expand, you go beyond classical EMI, EMC, strange things can happen. And thank you for your patience.
So do we have any questions from audience or Zoom? Okay, if not, so let's thank.
So everybody understood everything, or no, anybody understood nothing? So, but anyway, it is far too much for a 40 minutes talk, and you all want to go to lunch, as I can feel or smell. And so take it as an appetizer for EMI, EMC. If you have any questions, contact me or contact Daniel Valuch, who is now officially in charge for it. Or if you find his email address, Fritz Schwanzer. And we are, so the older guys are still quite active and happy to help you. And if you have any questions or suggestions or problems, many things can be done on the distance. And if you read these slides quietly, it contains a lot of highly compressed information, and take out, it's like a buffet, take out what you like, and the rest you forget.
Dear Fritz, thank you very much. This is Gökhan. 100 and something slides.
106 slides, yeah?
Yeah, full of acronyms. Maybe it's a bit heavy at lunch hour.
Yes, it is full of acronyms, and it's not meant that you really understand everything in the first go. I said this in the beginning. It gives you an overview. It tells you what we have suffered, and anyone who is building accelerators will suffer one piece or several of this big cake sooner or later. And that was the message behind. And I do apologize having this talk, which was last time also given in 40 minutes, no, not last time, it was given in between in the EPFL Lausanne, and but also some slides skipped. But it gives an overview, and that's the whole essence of it.
Yeah, maybe what we can do is we can go over your slides quietly in our free time, and then you can pay a visit to a lab if you can in Turkey, which is trying to build an accelerator, and then you can inspect and do the police work on the ground. We'll be very.
This is you know, at CERN we don't have a policeman, we have a commissariat of 25 policemen. And so they always have lots of work to do. No, one can do a lot first by electronic communication. And there's a number of questions, an exchange of questions and answers one can do. I just wanted to make you aware what can go wrong will go wrong. Try to avoid the mistakes in the beginning. You will not be able to avoid all, but I'm sure everyone who is working with a living machine has experienced EMI, EMC stuff in one way or the other.
Thank you very much.
So let's thank our speaker, Chris Kaspers, again.
Thank you.
So now I have realized that there is another very short talk. It is from Sedat Arı from Baysal University. So Sedat, are you there?
I am here. I am writing.
Okay, can you share your screen?
Okay.
Okay, you can make it full screen. Yeah, go ahead, please.
Hi, everybody. I am Sedat. I am planning to talk about our new generation patented flame detector technology. This technology is faster, more accurate, and more sensitive, innovative solution for the fire detection. The problem is that forest fires never stop on our planet for last years. Fires cause loss of life and property, as well as the destruction of large forest lands. In addition, fires cause great destruction in pool, station, and factories. All solutions offer faster, farther away, more accurate, and wider angle of flame detection. In addition, as standard, it can warn the user with sound or light and can make SMS or phone call. Actually, this technology is based on the UV detection. The fire detection with an early warning system will basically consist of 4 modules. There's one, a light photon sensitive gas chamber, pilot the detector volume. 2, thin conductive wire passed to the gas chamber and apply voltage. 3, a hemispherical filter surrounding the gas chamber. 4, signal processing mechanism. The wavelength of UV light emitted from the flame is generally in the range of 108.5 and 260 nanometer, except for some special types. This range is often blocked by the atmosphere layer, so all gases flame detector has been successfully tested indoors, outdoors, day and night, in all weather conditions. Working process is like a Geiger-Müller. We tested ethylferrocene and triethylamine as photocathode vapor. And we are using synthetic quartz or fused silica as detector window. These are transparent for UVC. The indoor temperature of detector is fixed at 40 degrees with an electronic thermostat circuit. In addition, the circuit board of the detector contains a DC-DC converter so that 1200 volt DC voltage can be applied to the anode wire. As soon as a flame or spark occurs, some of the photons emitted in all directions enter the detector volume. The incoming photon ionization, the photosynthetic gas in the detector volume, and the ejected electrons moved toward the wire by being caught in the electric field where the thin wire with which voltage is applied. Photons approaching the wire generate a signal by inducing a charge on the wire. The generated signal is converted into desired stimuli with an electronic module to be developed as a signal processing mechanism. The signal processing speed of this electronic module is as important as the detector's signal generation time. There are electrical connection and gas inlet-outlet valves on the sealed detector cover. In addition, a signal processing module is designed on the outside of the cover. You see the photos of the primitive prototype of our detector. We have passed quadrupole anode design from single line anode. This prototype has some sealing problems, but it is working well actually. And you see the another anode cathode design for our detector. We tried different geometries, different anode cathode systems, coated UVC transparent cathode, for instance, silver nanowire. Finally, we optimized a geometry, anode cathode mechanism, etc. Performance test of the flame detector's prototype at various distance between 1 and 100 meters in the same environment, open and closed, and at the angle have been successfully carried out, and the tables and graphics containing the results can be seen in the figure. Performance tests of the flame detector's prototype were carried out at various horizontal and vertical angles in the same environment, open and closed, and distance to meter. At the same distance and angle of the flame detector prototype, day and night on a cloudy, misty day, day and night on a clear, sunny day and night indoors. Performance tests have been carried out, including the tables and graphs containing the results. The present is over. Thank you so much for listening to me.
So, Sedat, I will say it in English and then I will translate it for you to Turkish. In a small lab, we are doing very good things. I am very impressed. So, a lot of silicon everywhere with around the metals, but it's a good detector for ultraviolet. And then it is good, very good. Yaptığınız iş çok güzel. Lütfen devam edin.
Teşekkürler, sağ olun hocam.
Yani basit şeylerden çok güzel şeyler yapıp patentini almanız çok çok hoş.
Çalışmalarımız halen devam ediyor hocam. Güzel gelişmeler de oluyor. İnşallah yakın zamanda daha iyi çalışmalar yapacağız.
Cool. Do we have any questions from the audience or Zoom? So if not, let's thank Sedat Arı again.
Thank you so much for listening to me.
So this is the end of our Congress. Before the end, we would like to give 2 certificates to So we invite the president of the scientific committee, Gökhan Önal, to give his certificate to Professor Erkcan Özcan. And next to Veli Yıldız. So this was the end of the conference. So maybe a last word from, no last word. So the last word is stay safe, stay with the accelerators, lot of beam, no radiation. So